Good. Okay. Well, yes. Okay. So can someone wake them up? Okay, we're awake. We're awake. We're here. So yeah, welcome everyone. Oh wow, there's like 127 people that are here already. Very cool. Okay. So welcome everyone. Like today is a very special day. It's like, I mean, it's sort of a disservice to call this a talk because it ended up turning into more of a mini conference. So we have 6 speakers today that are all like some of the people I admire the most, like doing very interesting work in open source. We have like Zach Wentz from PyTorch, Davide Tetsughini, also from PyTorch, Sania Bhutani, also PyTorch, Louis Tunstall from Hugging Face, Ben Burtonshaw from Hugging Face, and Daniel from Unsloth. So I think I counted, basically, I did this earlier. So there are 7 basically mini talks today. So Daniel and Louis will be talking like multiple times. I expect this whole thing to run for about like 2.5 hours to 3 hours. So, stick around, get your lunch, like come hang out. But yeah, like without further ado, I think our first speaker is going to be Daniel. Daniel, please take it from here.
Yeah, thank you. Thanks everyone for joining. Yeah, so like, our program.
Daniel, we can't hear you.
Wait, can you hear me?
Oh, we hear you now, yes.
Oh, wait, can you hear me now?
Yes.
Okay, yeah, okay, cool. Well, in terms of the program, so, there is a lot today. But yes, as Mark said, there will be all mini talks for everyone. So like, it's not going to be boring. It's going to be very, very fun. But like at the first step, I'm going to be talking more about like, introduction and intuition for reinforcement learning. So yeah, hello, I'm Daniel. And yeah, we allow you to like, what is Unsloth? We allow you to train and run language models locally. Definitely check us out on GitHub. Yeah. But like today, I'm going to talk about reinforcement learning quick takes. Mainly like, I always have like questions. What is reinforcement learning? What can reinforcement learning do? And what it cannot do? So I broke it down into like different sections. And I'll go to like, I'll just go through each one separately. And each of them are related to each other. So they're not like, they're not like disparate. They're all correlated with each other. So the first one is like, reinforcement learning is essentially efficient in context learning. So for example, because you guys are from GPU mode, like for example, we ask a language model to create a Python function to do fast matrix multiplication. So like if you ask, GPT-5 or Gemini or, Claude to do this, it should create some sort of function to generate, some sort of like Python function to do matrix multiplication. So obviously you should not use, you shouldn't probably do it in Python, obviously do CUDA or, even like, C++ for like CPU type workloads. But for now, let's just assume it's just a Python function. And, if you call ChatGPT, you should probably give it more constraints. For example, tell it to place the function between triple backticks, like for example, on the left. And yeah, like after you call it, like, for example, if you use DeepSeek R1, for example, you have like a think token, I need to create a fast matrix multiplication, blah, 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 right? And it does output some sort of algorithm that does this matrix multiplication. Yeah, and so you don't just call the language model once, you call it many, many, many times to generate, different algorithms to do matrix multiplication, right? You get your first one, the second one, the third one, you get many, many, many different ones. And the goal is to call the language model so many times until you get the best one. That's kind of like how you do, how you get the best matrix multiplication algorithm. And then after you generate all of these examples, you put all of these algorithms through a RO environment, some sort of verifier, some sort of tester to test if these implementations are good or bad. So you can't just like, take the language model's generated code, and just use it. You have to test if it actually works, how fast is it? Is it like effective? Are there bugs in the implementation? And then if you put this through a, environment, the goal is you want to like time, is this slow? Is this fast? What is the error rate between the true matrix multiplication algorithm between, matrix A and B? So you need to like calculate all of this. And in the end, you output some sort of number, right? So like, for example, the first one is pretty good, right? Torch, matmul, like, okay, that makes sense, plus 10. The second one is like a NumPy product, which also works, right? A NumPy dot. But the problem is it did not follow the instructions, right? So it didn't follow the instructions. We need to put it between 3 backticks, right? There is no backticks over here. So we -5 for this, right? It doesn't actually follow the style. And then the last one is definitely wrong. So we give a score of -100. The reason is because, the output is totally wrong, plus, 0.001, something like this. So this is kind of how we evaluate these, implementations by just like shoving some sort of like, shoving through a RO environment or a verifier or a tester. And then you get out some sort of number. And so like, the way to score this, right, after you score all of these, you then do the prompt again in the language model and shove, place in, the examples into the actual prompt, right? So this is the second prompt you're going to ask the language model again. And so previously, we said create a Python function to do fast matrix multiplication. And then you add something to the prompt. You say, I created some for reference with these scores from -100, the worst, to 100, right? And you put the good one, you put a bad one, and then you say, your job is to make a better one and place it between the triple backticks. And that's what you do to ask the language model. And you would assume like, this process will go on forever, right? You will call many GPUs, you continuously call the language model multiple, infinite times until your score continuously goes up. And so that's why I like to call like, reinforcement learning is kind of like efficient. So this is an example of in-context learning where you call the language model multiple times to generate examples. So you might be wondering, okay, this can go on forever, but you should employ like some sort of pruning method, some sort of like, should we don't put every single example inside of here, maybe remove some of the bad ones, will this go on forever? Can you make this a very, very, very long prompt? That's the main question. And there is like some sort of, long context benchmark called, I think, long arena or long context benchmarks, which show that generally models do better and better over time for long context, but the accuracy is not, it does degrade over time. So even Gemini, for example, has 1 million context lengths. At hard mode, if you want to find 8 needles, it does decrease accuracy to like 20%. And so, yes, over time, these models will get better and better and better. But remember, the goal is we want the model not to utilize all of this long context, just to like solve one small little problem, like this algorithm. And so with reinforcement learning, the trick is reinforcement learning is essentially efficient in context learning. You do the same approach as before. You call the model many times to generate the fast matrix multiplication algorithm. So you do the same as before. You have an RO environment or a tester to get like a reward for each of these implementations. So these are the numbers. But then the trick is you reward every single line or every single token with the same number that you find. For example, the first example was +10. And so we reward every single token or every single line with +10. And so that's the trick of reinforcement learning. You don't just like reward the whole thing, like the whole implementation is +10. You reward every single token with +10. And then every single token that was bad, the bad example, the +0.0001, you just reward everything, every single token, every single line as -100. And then the trick for reinforcement learning is now we update all the weights with backpropagation by using these numbers, right? So this is a good one, this is a bad one. And then we just update the weights with backpropagation. And then the trick of this is there is no more long context needed. You do not need to like shove in, all of the examples into the context. You just ask one question, how do we create a fast matrix multiplication algorithm? And you just let backpropagation and gradient descent do the work. And so reinforcement learning essentially is a more token efficient approach than in context learning. And, normally how I like to frame it is reinforcement learning is just patience is all you need. You just need to wait, just wait and wait and wait and wait, and you will get a good result at the very end.
So, Daniel, I had two questions on this. So, like, I mean, so there is a simpler baseline, right? Like the simpler baseline is you just have a base model and you do like pass at k, where k is like a very large number. This seems simpler. It seems less efficient because like k is hard. But like, could you speak a bit more like what you mean when you say RL is more efficient? Because most people would say it's not efficient because you only get one bit of information for a very long rollout. So could you sort of like help me understand this intuition of efficiency a bit better?
Yes. So reinforcement learning is less efficient in general than like, for example, than supervised fine tuning. Because like, for example, over here, right, we just allocate everything as minus 100. It's probably not a good idea to like, make everything as minus 100. For example, like you get a final reward and you just make every single token as minus 100. For example, this line, right, I need to create a fast matrix multiplication, algorithm or something. This probably is good, right? You should not reward this as minus 100. It should be like plus, 50 or something, right? Or like, return a, the symbol for matrix multiplication B, that's correct, right? But the only problem line is this line, right? The plus 0.001. Okay, put extra dot. But yes, that's the problem line. And that should be like minus 100. So in general, reinforcement learning, it's not efficient, not because it's not efficient, it's because at the very end, we reward every single token with the same number. And so we could actually make this process much more efficient. I'll talk about this. It's called process supervision.
Yeah. So this is interesting. So like, I mean, this is like, but this would work for SFT as well too, right? Like if basically you could reformulate, I don't know, like, because you could view this as a translation task from English to a fast kernel code, or you could view it as like, well, let me reward individual tokens, and then basically this is like a richer signal. And I see, okay.
Yes, correct. Yes, you could pose reinforcement learning as just supervised fine tuning. So, for example, instead of like just predicting the next token, you can like change the loss, I guess, to like just. I guess it's kind of like DPO, for example, like what is good, what is bad, but it's more like a dynamic version. So reinforcement learning, you don't need. It's like more like regression, I guess. Like you're trying to predict a number like reward, and then you're just updating the weights. But I will talk about process supervision, I think, like in the next few slides. All
right. So I think someone's already asking about GRPO, but I assume you'll be talking about that.
Yes, I will be talking about
I'll let you keep going.
Yes.
Okay.
But yeah, like essentially, I like to call like patience is all you need, or like luck is all you need. At the very, very beginning, reinforcement learning will get zero reward. It won't work. But then you just have to wait and wait and wait and wait and wait until it will like you will get some reward. And that's the trick of reinforcement learning. You just have to wait. And the next topic is like, but you don't just want to wait forever, right? And so the goal is reinforcement learning is inefficient. Yes, it's not very efficient because of this problem, right? You just allocate minus 100 to everything. However, it's not dumb. So for example, at the very beginning of training, assume all the probabilities are like equal probability, right? So like, 1 divided by whatever the token size is. So 100K, for example, right? Every single token is equal probability to be shown. When you do reinforcement learning, you will get bad answers. And so the goal is you want to penalize these bad answers. And so the probability of getting these answers becomes less. And then you want to like increase the probability of the other answers. So the bad ones, we reduce the probability. So this dent, and then we increase the probability of good answers, or like, the answers that we have not seen yet. And so over time, if you keep doing this process, you will keep generating bad and bad and bad answers. And so the whole landscape of the probability distribution will like essentially shift and change with this approach and with reinforcement learning. And then once you get a very good answer, there is like maybe somewhere in this high dimensional probability distribution, you will increase that probability dramatically. And so the rest will like decrease. So this is kind of like how you visualize reinforcement learning. So essentially, it's not like just you're like forcing the algorithm to like learn, everything is bad. It will just like forcibly not produce that one answer. It essentially tries to like change the loss. It changes the probability distribution for every single other answer. So that's why like normally how I like to say is like reinforcement learning is it's not dumb. It's just not very efficient. But it works. It definitely works. So the next point is like, for reinforcement learning to work, the probability of a good answer must be greater than 0. If your answers are always 0, right? So for example, if you keep waiting forever, but you never get a reward, reinforcement learning will not work. So this is the most important factor for reinforcement learning. It must have a probability of a good answer to be more than 0. This is the most, I would say this is like a law for reinforcement learning. And so like, for example, there are many, many problems that reinforcement learning can encounter that you might also always get 0 reward. For example, your formatting might be wrong. You might have to do like some priming or warm up to like, force the reinforcement learning algorithm to generate the format. You might have to do some supervised fine tuning. You might have to do some pre-training, or the problem is just way too out of distribution. So all of these problems can come up, and you just have to I guess you have to pray that there is some probability of the good answer, and it must be more than 0. If it's 0, then you would just be wasting compute and just waste, just sitting there, and then reinforcement learning just does not work.
Okay, so Daniel, I had a question for you then, which is, okay, perfect. No, go to the next slide. It's actually
okay, yeah.
Okay, so something I found very unpredictable is let's say you're like a middle class researcher. You have like a bunch of GPUs, maybe a couple of nodes, and you're trying to figure out, you have a task that you care about, and you're trying to figure out what's the best way to allocate your compute. These days, I found it kind of non-obvious, how many GPUs should be reserved for synthetic data generation, how much should you do for fine-tuning, how much should be for RL. It's not entirely clear to me how to go about this. So do you have some intuitions that have helped you do this?
Yes, that's a great question. So I guess this plot kind of makes a bit somewhat kind of sums up your question. For example, in the olden days, you would do pre-training, then SFT, supervised fine-tuning, then some post-training phase. This is the general workflow of everyone. So your question is more what is the bucket size? How do we allocate resources to which bucket? So I guess this one, right? So you could, for example, theoretically, just start from a random initialization of the model. And somehow train the model just doing reinforcement learning, or doing something to go to the final model. And so the question is, how do we actually allocate, resources during this process? And so in the olden days, what you would do is you would do some pre-training to go to this space. You would do some supervised fine-tuning to go to over here. You do some preference fine-tuning, and then you use reinforcement learning to get your final model. So this is kind of the process. And so the question is how much percentage do we spend in each of these stages? And my point is you should spend the majority of your time in pre-training. You should do fine-tuning, some sort of supervised fine-tuning step, and then you should spend some resources of reinforcement learning. But in general, all of these steps are very important. And then the reason why they're all very important is because you want to make the process efficient, and not waste resources. For example, you could, bypass pre-training and just go to the RL model, right? So you don't need to do supervised fine-tuning. You don't need to do preference fine-tuning. Just skip everything. And for example, deep speed zeros, something like this. And I actually do not suggest people to do this because this is very wasteful. And the goal for artificial intelligence, the goal for deep learning is you want to efficiently allocate resources. And in my view, all of machine learning is just efficiency, right? How do we make everything more efficient? And so I would suggest people to do all of these phases. Maybe allocate 10% of compute to RL, 10% to supervised fine tuning, and then the rest for pre-training. So 80%, 10-10. Yeah, I'm not sure if that kind of answers the question. Yeah.
No, it does, and I'm thank you for giving actual numbers. I think that you're putting your money where your mouth is there. So I think that's very helpful. Yes, thank you.
To be honest, it's more 99% should be pre-training, and then 1%, 0.5, 0.5. However, if pre-training the loss doesn't seem to be decreasing, then obviously you need to then I guess you have to allocate more time. But the trick is for example, when you do pre-training first, you can always expand, increase the time you want to do it for reinforcement learning. So it's more you just have to do a good pre-training, and then you could spend more time for RL or SFT. Yeah. Yeah, so the next one is yes, as Mark was talking about process supervision, for example, RL is not efficient. The main problem is when you do reinforcement learning, you assign the reward -100 to every single token or every single line exactly the same. And that is a problem for reinforcement learning. There is a method called process supervision where you manually check which line is good, which line is bad, and then you allocate different numbers for each of the lines. For example, these tokens, the think token, whatever, it's not that important. So I just allocated reward of 0. This in the prompt during the generation, during inference phase, during the inference step, it does say I need to create a fast matrix multiplication algorithm. So this is actually not that bad. And it does follow the format. And so we plus a few points, but then we do allocate -100 because it did a wrong, this step was wrong. And so like this is called process supervision, where you're like, look at the, you don't just allocate -100 to every single line or every single token. You actually look at, which token is good, which token is bad. And so how would you do this? Unfortunately, what people do now is you have to have like, you will ask many, many, many people to like, look at the outputs, manually, humans have to manually label this. And so there is a way, instead of doing this, instead of asking humans to label it, why don't you ask a language model to label it? So this is called like a, LLM as a judge or something like this, where you just call the language model, to label this for you, right? So the prompt will be like, to like ChatGPT or Gemini or Claude, is this line good? Is this line good? Is this line good? Or, is this line good and relevant to the original question? And you let the language model label these numbers. And so this is like, this could work. You just call the language model many, many, many times and it will label this for you. But then we encounter a big problem, which is essentially you might fall into the trap of reward hacking. And so one of the biggest problems is if you do this process supervision approach, you ask the language model many, many times to label it, you might also encounter the language model not labeling it correctly. For example, it might actually cheat. For example, it might delete the timer in the, in the function. It might edit A to be 0. It might edit B to be 0. It might do many, many weird things. And the language model might still label this as good. You actually don't know what it will do. And so this is one of the biggest problems of reinforcement learning. And this keeps most researchers awake at night. Like, will RL just go into the reward hacking trap? And, essentially RL will not work. And so this is still an open question. Another one, for example, is corruption, where it will actually try to corrupt your computer. For example, it might, do RM-RF or something. I don't know, something like this. And so one of the biggest problems is it might actually edit, your computer to try to, cheat its way out. It might even say in the prompt, like, some weird formatting, like, something else inside the prompt. And so this is one of the problems for reinforcement learning. If you want to automate it, it might reward wrong signals. But in terms of like different flavors of reinforcement learning, at the very, very beginning stage, we had PPO, which was, I think this was invented by OpenAI researchers. And so like, you had many different types of models for PPO. Yes, sorry.
So sorry, but before you go there, let's talk about hacking for a second. I think the hacking point like has a sort of simple answer at small scale, which is like, look at your data. You're like, oh, like you're doing CUDA kernel code gen. How many important kernels are there? Like, a few hundred, look at them. But like, I really don't buy that. Like, like something like Claude Code, for instance, like for me, it was very challenging to imagine that like, Boris is like looking at every code snippet being generated. Yeah. So how do you end up making these things like reliable at scale? Is it kind of like what you said, just LLM as judge and you audit the LLM as judge, like, or kind of what do you suspect is the secret sauce for a lot of these large scale audits of reward hacks?
Yeah, so LLM as a judge can be useful. So you can like ask a language model, does this implementation look correct? Are there any bugs in this implementation? You can like, essentially can call a language model many, many times and give like some sort of number, right? So for example, if you give this language model, like, does this look correct? It will probably say no, because it does something else. And so it will reward it like -100. So yes, you're correct. In the normal days, like, if you have like few data, you should manually inspect it. But then, because of reinforcement learning, it automatically generates everything. You don't want to like, it will be a very tiring job to inspect every single step, every single data point. Normally how I would like to do it is like, maybe do a sampling, sample 1% every single 10 turns to see the generation of your model. And then if it looks wrong, I think you should just terminate the run and see what happened. So generally that's how people do it. You just like sample, you look at the output every single like 10 turns, look at like 10 examples.
So like reward hacking is more of a property of the model being dumb, not of the model being very clever, would kind of be your thesis here, right?
So reward hacking, I wouldn't say the model's being smart. I would say the model's just being, I would say actually the human who wrote the instruction is probably incorrect. Your instruction has to be more clear. For example, like, you should like mention, do not do this or do not do that. But then I guess if you keep doing this, your system prompt might be very long. That is also a problem. And so like, I guess it's more like, the human has to like guide the model, the RL process. Yeah, I mean, you could imagine, for example,
but it's a positive sign that we can detect this early, is really
yes,
your
definitely.
thesis. Like, it's not something that's sort of emergent as the model becomes superhuman near the end of a very expensive RL training run, which would be very annoying. Okay, I see.
Yeah, definitely. Like, most training runs, you need to inspect it. Like, every single 10 turns, look at the generation, look at the inference output. Don't just let it run forever. That's probably not a good idea. And then, every single 10 turns, does it look correct? Does it, like, I guess we still need humans to like inspect if the model actually is correct or wrong. And then if it looks wrong, just terminate it, or like, go back to the previous checkpoint. And you maybe edit it somehow, or like delete. Maybe another way is to like delete the bad responses, like, maybe add some sort of filter to like, guide the model's reinforcement learning process. Yeah.
All right, let's keep going. Yeah, thank you.
Yeah, but like in terms of PPO, like, there are many different parts of PPO. But then we had GRPO, and essentially GRPO is just a more efficient version of PPO. Essentially, we got rid of the value model, right? Delete it. And so GRPO essentially just made it much more efficient to do training. And then with reinforcement learning with verifiable rewards, or RLVR, instead of having a reward model, so the reward model actually had to predict, what is the reward for this specific turn. Instead of that, we just had some sort of environment to check, to tell you if it's good or bad, right? So it's like some sort of like tester, some sort of verifier. And this is, GRPO with RLVR.
Daniel, sorry to interrupt you, but like your other co-speakers have things they'd like to say. So I'm adding Davide and Sanyam to the chat.
Oh, okay. Yeah.
Hi.
Hello.
Now you can go first. You can go first, please.
Well, I don't know. We kind of moved on from the topic. I was maybe I could add some color on the reward hacking part.
Oh yes, we can go back to that.
Yeah. So basically, like another way of seeing this, sometimes reward hacking kind of surprises you. Like for example, when we work on Llama, we had a model that was a very good model that surprisingly was very laconic. Like it didn't seem like he wanted to talk to you very much, but it tended to be quite accurate in benchmarks. And we ended up not shipping that model, although its benchmark score were a bit higher than the ones we ended up choosing. But so in general, I think that one way of seeing this, what's happening here, is that unlike supervised fine-tuning, in reinforcement learning, you're exploring, right? So you have your exploration, and then almost think of this as like water percolating in a way, right? It's going to find different paths and whatnot. And then it's basically just going to score them based on, what you said. So one way of thinking about this is that the search algorithm is going to give you exactly what you asked for, which may or may not be what you wanted. That's kind of up to you. And so anything that you're not specifying is fair game. One example, this happens constantly, and it's just a byproduct of search. Cool example that you can find on YouTube. I'll see if I can link it. Even a simple RL agent found a long-standing bug in Super Mario 1 that had been there for like 25 years, where when you jump, if you turn back after you jump, you have like one frame in which you're invulnerable. Obviously, nobody was able to exploit it, but certainly an agent can. And so if you we training agents normally to kind of play like humans, that's kind of underspecified, but we never say it in the reward function. The reward function is clear the levels as quickly as possible with a higher score as possible. And so the model will just exploit the shit out of it, because the sooner you clear a level, the more bonus points you get after you get to the flag, right? And so that's how you get to these like non-human looking models. This honestly happens even with humans, actually. There's a great example on Wikipedia on this, which is perverse incentives. So this example was from India in the 1800s, where they had too many cobras in Delhi. And so the British Protectorate had the great idea of saying, okay, I want fewer cobras. So what am I going to do? let's just have a bounty, right? Like bring me a dead cobra and I'll give you some money, right? So that's what you ask for to the process. And what you get is people breeding cobras. So by the end, they gave up on it, and therefore people just freed up the cobras, which are now worth nothing. So in the end, Delhi had more cobras than in the beginning of the process. And so this happens like constantly. So you're kind of moving towards like almost dictating a policy in a way, like not a policy in the RL sense, in a policy like a policy maker, like you're writing a law, right? This literally happens all the time with laws. People find loopholes. And so the search process will kind of do that. And so, yeah, you have to monitor and you have to iterate. It's true that you cannot possibly read everything that the model produces. You sample, you can do some like aided search. For example, you get like vibe checks, and then you're like, oh shit. Like, for example, this is what we did with Llama. Like, these answers are kind of short. All right, so let me compute average length of 1,000 responses. I'm not reading 1,000 responses, but if I get the average length, it's lower. It's kind of confirming kind of my vibe, right? So you start with a vibe, and then you use filters to kind of see if that's the case. It's still kind of more art than science. I think this is also an area where an LLM itself can do this eventually. But hopefully you get the gist.
Yeah, I was gonna say, like, I actually agree. Like, it's more like you're trying to say the environment is the problem. Like, there are some sort of like bug. There's like some sort of like, as you said, the Mario example. There's like, some hacks. You could like, yeah. I guess the environment itself has like, specific things you can like, utilize. And yeah, like, even humans have this problem. Like, we can like hack our way to do something. Yeah, I guess I agree with that point. Yeah.
I'm so sorry to the audience for interrupting Daniel's energy, but
No
maybe it's a question or a comment. I always had the conception that for some reason, reinforcement learning is like this idea where you don't have to be involved in data prep. But the more I've played with it, and like to Davide's comment, it feels like this is like more involved. In the sense, once you like achieve these rewards possibly successfully as well, then you have to figure out how to solve these questions for harder questions. And sometimes when you're starting reinforcement learning, you give like very tough tasks to the model, which it like you say luck is all you need or like patience is all you need, but sometimes it's like the task is so hard it never gets it right. So do you feel like there's also like more data prep involved as you like train the model, you give it easier questions and you give it harder questions? Because I've seen this come up in some papers.
Yeah, I think that's called curriculum learning. I think like, essentially you can like guide the process. You do like some easy questions, and then over time you give it harder and harder questions. Yeah, that's actually pretty smart. I think like, I think that's actually what people should do. Like don't give like hard questions at the very beginning. I think like one of the things I said, like, if the probability of a good answer was 0, for example, if you ask the model a hard question, the language model would just never learn. So you should, as you said, like, maybe do some easy questions first and then move over, increase the difficulty as time goes on. I think that's what people do. I'm not sure. But if people are not doing that, you should do that. Yeah.
So you probably don't want probability of 0 and probability of 1. You want it to be like somewhere in between of that.
Yes, correct. Yeah. Yeah. Definitely not probability of 1. Then I guess the model will just output the same response over and over again, and it won't be very useful. Yeah.
Okay. Thanks.
Yes. Okay. But yeah, so like in terms of the, like for example, this RLVR process. So essentially previously, you had a reward model. So this is actually a model to predict the reward for a specific, sentence or a specific token. Instead now with RLVR, it's an environment. So essentially it's a tester, a verifier. This could be, for example, a formatting check. Does this code execute or not? A regular expression check, or the LLM as a judge approach. Or another way is if for environments, you can also use open environments for the actual environment generation. So for example, this step, this environment step, you can use open environments, which has a collection of many pre-built environments. For example, in this notebook that we have, you can use open environments 2048 game to actually play the 2048 game with reinforcement learning. Right? So at the very beginning, it doesn't actually, the goal is to generate an algorithm to solve 2048. At the very beginning, it doesn't do very well. You might get timeout issues. You get like exceptions. It just doesn't do very well. And then over time, it might actually generate some sort of strategy to play the 2048 game. So it will get better over time. And so open environments is a collection of many environments which you can use for, for reinforcement learning. In terms of like other updates, like, from the Unsolved side of things, we are going to be releasing ultra long context reinforcement learning, which is coming this week soon. So this is directly compatible with open environments. This will make training even much more efficient and much more better for reinforcement learning. And another important point for reinforcement learning is you need to make inference extremely fast. Previously, if you want to, normally what happens is as time goes on, inference will take 99% of the training run, and training will only take 1% or less. And so the goal is, if you want to make reinforcement learning faster, you need to make inference faster. And so, we spend some time trying to make inference faster. So, Llama's faster, GPTOSS is faster by using Unsloth for reinforcement learning. And also ultra long context, as models get more and more capable, you need to increase the context length. So, as the problems get more and more harder, you need to fit larger and larger context lengths inside the window. And so you need to focus a lot of time on trying to make this possible. And, finally, my view is, most of the large labs, their goal is reinforcement learning will automate reinforcement learning. So essentially the goal is, to create so many different types of environments, to do weather prediction, to play games, to do, stock trading, I guess, to solve math equations, but also to, do training faster, right? You can essentially make an environment for all of these characteristics. And this is what you call the intelligence explosion, right? So some people think AI can automate AI research. And once you get to that point, then reinforcement learning can scale to like AGI, for example. So this is kind of the viewpoint of the large labs, for example. And, some people think this might happen. Some people might not think this will happen. And so this is more like a wait and see approach. Can we allocate more resources to reinforcement learning to make, to reach this intelligence explosion phase? But I guess thanks from my side. That's kind of the main points I wanted to say. Definitely check us out on GitHub. And I also have like a conglomeration of stickers, of random unsolved stickers. But yeah, thanks for this part.
Wonderful. Thank you, Daniel. I guess Daniel will be coming back for a second talk, in this current workshop. So if you enjoyed this, you'll enjoy next. I think the next speaker was, remind me, was it Lewis? Let me see. I think it was Lewis. Yes.
Yes.
All right,
Can
Lewis.
you see the screen?
Yes, very clear.
Awesome. Cool. So yeah, thanks a lot for having us here, Mark, and also thanks to Daniel for giving this awesome introduction to reinforcement learning. So Daniel gave a really nice overview of how reinforcement learning works, and also how it's become a kind of important part of post-training toolkit. And I think almost every model now that is released has some degree of reinforcement learning in the pipeline. And there's a really nice picture here from the Olmo 3 paper from Alan and I, where they kind of show the various stages that go into post-training. So typically you have some SFT, then you might do some preference alignment with DPO, and then typically some RLVR. And there's this whole process that Daniel kind of alluded to, where you kind of have to filter your data to get good prompts that are kind of learnable, that they have the right difficulty level and all that kind of stuff. And this works really well. We know from many open recipes that you can significantly improve the performance on various capabilities like math and code by doing RL. But there is a kind of common problem. And the common problem is that at some point, your reward will typically plateau. And what this means is that you reach a point where the kind of set of prompts that you've got, and perhaps just the capacity of the model, can't really go beyond the ceiling. And so then your kind of choice is okay, I could take a checkpoint of a model and then find some more data and keep doing more RL. But in general, this kind of idea of just doing RL static data sets is a bit limited. And on top of that, like the kind of, let's say, the real world, like the real world applications of language models are far more complex than just, solving like a math problem. In reality, the kind of models that we use today, they have lots of interactions with different systems. So if you're a programmer, you've probably used Claude Code and Codex. And what you can see is that these kind of like systems are like interacting with like files, with the debugger, maybe interfacing to APIs, all that kind of stuff. And so there's like a whole range of different signals that now the model has to deal with. And if you're only training on like kind of static data sets, it's pretty hard to kind of teach the model how to kind of generalize to these like different domains. And so the sort of common paradigm of like going beyond doing RL on like static prompts is to introduce this concept of an environment. And there's a really nice picture here from Meta's code word model. This was a really cool paper where they showed how to basically do RL at scale with like thousands and thousands of environments for coding. And the basic picture is that you have some prompt, you give it to your agent or your model. It might do some reasoning, like Daniel showed with the matrix multiplication to figure out how to make things fast. It will generate some output or an action. And then you feed this into the environment, where the environment might be, like a compiler, or it could be, some unit tests. And then that environment will then give you a reward and some observation and some other information. And then you kind of loop this over, and now the agent then, based on that kind of information, now has to take another reasoning step, another action, and then so on and so forth. So basically you have this paradigm of like taking actions, observing the output from the environment, and then learning or backpropping to improve your ability to take those actions. So these environments, as I said, they could be things like unit tests, but nowadays, right, we want these things to be kind of useful. So they can be, for example, web browsers, and there's a really cool open source environment called BrowserGym, which basically creates a whole bunch of different tasks around how to get like a language model to basically navigate through the web. And this is the thing that I think many people kind of are like hopeful that eventually we'll have agents that can sort of take actions for us, like booking Airbnbs, flights, all that kind of stuff, or interfacing with Excel on the web, all that kind of stuff. So this is like a really good example of a real world environment. The one that is also very like popular for like software engineers is to have something like MCP, or the ability to say use MCPs or skills, things like this. And a very kind of interesting direction from mostly the Chinese labs has to basically create kind of simulators of these MCP servers, where essentially an LLM is kind of pretending to basically be an API, and then the agent is interacting with these like simulated APIs to then figure out how to get better at using these servers. So those are a few examples, and one of the things that is like kind of alluded to in the discussion with Daniel was about this like curriculum learning. So if you're using like a static kind of data set, the kind of, let's say, the difficulty of the problems is to some extent fixed like a priori. And what you really want to be able to do is like have the ability to kind of give the model like on demand the kind of most learnable prompts. And so environments for RL give you a kind of natural way to kind of provide the model kind of every batch or every training step kind of most appropriate problems. And there's a very nice paper that came out like just in the last year called RLVR, where instead of doing reinforcement learning with verifiable rewards, you do reinforcement learning with verifiable environments. And they showed that, for example, here, if you take something like an existing reasoning model and you try to kind of squeeze out a bit more performance in math using like standard RLVR, you kind of really are kind of stuck at like 0.5%. But if you have this like diversity of environments and problem difficulty, then you can get some significant improvement, which is nice. So these kind of three things of like having real world environments, the ability to kind of naturally have a curriculum makes this paradigm quite compelling. And obviously, like, OpenAI and Anthropic and, the other kind of frontier labs, they were the ones to sort of pioneer this with things like O1 and later O3. But, since then, many of the sort of, big Chinese labs have been releasing not just the models, but like kind of detailed tech reports into how they post-train them. And a really good example of, using a lot of environments comes from the DeepSeek v3.2 paper, where they mentioned that they basically created like, roughly 2,000 like different environments and over 85,000 different tasks. And then they use this to basically, improve the capabilities of DeepSeek v3.2 across like a wide range of different agentic kind of benchmarks. And you can see here in this kind of graph from the tech report that you've got this kind of like, performance that comes from SFT. And then this blue curve is like kind of showing like through the course of training how one of these benchmarks called Tau Bench, is improving through this kind of RL process coupled with these environments. Since then, the labs have kind of been trying to outdo each other. So there's Minimax. They have a really nice tech report, or it's more of a blog post, where they basically show that if you scale this like really, really fast, so now it's not just like 2,000 environments, they have like over 100,000 environments, which they kind of created from GitHub repositories, and then basically the repository itself is then an environment. So it's kind of like, imagine that you've got like an IDE, so you can like, you have a task like fix this bug, and then the agent or the policy has to then, navigate the environment, navigate the repo, fix the problem, make sure the test pass, all that stuff. And, at the time of the release of this 2.1 model, you can see that across all these different like agentic evals, this process does work. And in particular, they sort of mentioned that they observed this kind of like, positive correlation between like scaling the number of environments, but that they're far from reaching convergence. And so this kind of suggests that like, we're sort of early on this whole topic of environments and how far you can really push, the performance of models across like various, domains that we care about by, scaling compute, but also by scaling the diversity of environments they're exposed to. So, where do we get these environments? Today in open source, they're usually scattered on GitHub. And this reminds me a lot of like the early days of the transformers. Some of you may be too young to remember this, but there was a time when the kind of only way to get access to model weights was to go to GitHub, find like a URL to some Google Drive, try to download the weights, try to run the code, but it never really worked. And that was like a big motivation, at Hugging Face to create the Transformers library to sort of unify all these like disparate ways of like, training transformers and also sharing them in a kind of standard way. And there are like other projects in the community trying to kind of unify the environment ecosystem. But we've got like our own kind of a take on that. And it's sort of like part of the motivation is like, how do we make, environments kind of like the first class citizens that, we already have like data sets and models. But, something like, the Hugging Face Hub, how do we kind of integrate this in a straightforward way? So this is like the motivation behind OpenEnv, which is a community project that was kickstarted by Meta and Hugging Face. And the basic idea here is to take the sort of, well-established like kind of paradigm for environments in RL that was, pioneered through things like OpenAI Gym and Gymnasium. And in this kind of like sort of setting, you basically have like three things that you need to kind of keep in mind. You have obviously the agent environment, but then you just want to keep track of like, the actions the agent makes, the observations that you get from the environment, and then the rewards, of course. And so your kind of like loop for these environments is pretty simple. You basically have a kind of environment that you're interested in. So something like Text Arena, which is like a bunch of text environments. You can basically pull these from the Hugging Face Hub, and then this will like, either instantiate itself as like a kind of Docker image or Docker container, and then you can like interact with it. Or as we'll see later, you can also just directly, send HTTP requests to the Hugging Face Hub and get your rewards directly from there. And so then once you've got your environment, you just have basically a loop, which is like, the agent takes some action, you feed that action into the environment, you get the result, and then from that you extract the rewards, and then the rest of the loop that Daniel mentioned, for RL follows straightforwardly. So an example that I'll talk about a bit later, more hands-on, it's kind of like a simple one, using Wordle, the game that I think most people here know about, where you start off with like a kind of hidden word that you have to guess, and you can kind of select, some candidates, and at each step you're given some like partial feedback as to whether the letters are in the right place, or are they completely wrong altogether. And the way it works, like in kind of an RL loop, is that you're going to basically instantiate your environment. You generate your rollouts, which are going to be basically your candidate solutions, and then you extract the actions from those rollouts, and then you feed them into this game, and then you get the rewards, and then that's it. So again, the kind of interface between OpenEnv and training frameworks like TRL is pretty straightforward, and it's been designed in a way that is kind of maximally agnostic. So it doesn't make any sort of strong assumptions about what the training framework is actually going to do with those rewards and how it implements different algorithms. And we have examples in a variety of different training frameworks, Unsloth and Agent Enforcement Trainer, which is again one of the goals of the project to sort of show that as a community we can build these kind of environments together, and then they can kind of be maximally shared across all the different initiatives to train LLMs. So I talked about this idea that you can pull environments of OpenEnv from the Hugging Face Hub, and the basic kind of infrastructure behind this is something called Hugging Face Spaces. If you haven't heard of Spaces, I won't try to sort of do a big intro, but basically these are kind of applications which run on the Hugging Face Hub. They have their own hardware, so it can be CPU or GPU. And these kind of applications, conventionally have been used for building machine learning demos. So things like if you want to have, for example, a chat interface for your model, or if you want to share some sort of cool way that your model can generate outputs. But this whole infrastructure can be basically repurposed to create environments. And so the way it generally works is that you sort of pip install the space as a kind of a module, like Git repo, and then you can pull this environment from the hub, and then do all the things I mentioned before. And the thing that I find particularly cool is the idea that you can use these environments kind of remotely. So if you want to run lots of different environments, it's a bit of a drag to have to kind of install everything or set these things up kind of locally. But having the ability to kind of quickly interface with these things remotely, I think is a very cool feature. And Ben later we'll talk about some benchmarks that he's run, comparing kind of what's the kind of throughput you can get both locally and remotely. So I mentioned that these environments are spaces. That means that they're essentially deployed on the hub, and they have a user interface, they have an API. But because they're a special class of space called a Docker space, they also then come with a Docker registry. They're Git repos, so you can version them like anything else, similar to having with models. And they also come with built-in things like authentication and so on. So one of the kind of cool things here is that now the same sort of things that we're used to using in the Hugging Face Hub around models and data sets can now be linked very closely with environments. And I think Sanyam will talk after me, showing you how you build environments. But in OpenEnv, it's quite straightforward. You basically have a CLI, you can init, and it will create a template of all the files that are needed to build these Hugging Face spaces, and then you can just push them to the Hugging Face Hub and then share them, with collaborators. So that's me for now. I don't know, Mark, if there are any questions at this point.
Yeah, absolutely. I think I had sort of one main question. I think this is in reference to the thing you mentioned on TeepSeek creating 18,000 environments. Presumably machines created the majority of those environments. Mm-hmm. And so in this setting, like, how do you think about like the quality of these things, like the sort of their propensity for reward hacking, measuring the utility of an individual environment as far as with respect to the entire post-training run? Yeah, just broad thoughts there would be great.
Yeah, it's a really good question. So indeed, I think from what is like at least publicly disclosed in these like tech reports, it seems that most of the emphasis has been on environments that are relatively straightforward to automate the creation of. And so as a result, that tends to be things like code related, like software engineering related, or tasks perhaps where you have like a final answer that can be verified easily. So, things like in mathematics, right? You have an easy way to kind of say verify the correctness. So what I've seen in a lot of these papers is they will typically create some real environments. Like they'll take maybe some MCP servers from GitHub, and then they will install them, set them up as Docker containers. And then this gives them a template to then basically use another agent to kind of create variants of that or different tasks, and then you can kind of then run this at scale. When it comes to more like real world tasks, from what I understand, this is still a very like artisanal enterprise. So there's discussions like in the rumor mills that like OpenAI and Anthropic pay hundreds of thousands of dollars for people to create things like a clone of Slack or a clone of Salesforce, because then if you RL your agent in this like high fidelity replication, you have a good shot that then people can then sort of integrate this into Slack without having to gather lots of data at entrance time. So the short answer is I think so far in open source, we're still, I would say, kind of like constrained to these environments where it's easy to kind of verify things. And it's easy to sort of set things up around GitHub repos, basically. But going beyond that, I think will require some big dedication from some groups or individuals.
I have one more question. I think Sanyam also had a question. So I mean, I'm old enough to like remember the Dota bots. Like, I think for me that was like a big field AGI moment because I'm a big player myself and I played against these bots and they just like destroyed me. And so there was sort of this meme at the time that like, well, all we need to do is collect more and more games, and eventually like this would sort of like give us a path towards AGI. But like that turned out to be sort of a research dead end. And so what would you say is different basically this time, where like you're describing something similar where people are creating all sorts of simulators, but this time people feel more convinced that this will actually work than we did 10 years ago. So why do you think that's the case?
Yeah, I guess the obvious difference is like in the Dota context, it wasn't an LLM controlling the games, and even like later, DeepMind, they had this Gato,
like the Alpha Star, like the StarCraft one and the Go one.
Yeah, but they also had a nice one. I think it was Gato, where it was like essentially trained across like many different games, but also like different kind of like robotic environments and stuff. And indeed, it also didn't lead to anything beyond that. My suspicion is it's probably because the LLMs weren't in the game, so you didn't have the flexibility to kind of benefit from all the kind of world knowledge that the LLM has ingested to then hope that you can kind of generalize, a bit outside the narrow confines of the game. I think here, like the sort of big push on environments is partly related to something that's discussed a lot around this, like, jagged intelligence. Like the idea that like most of the models that we interact with, they have like kind of spiky capability where like, they're very good perhaps on domains that, the labs have targeted to optimize. But then if you kind of deviate out of this, they tend to fail in this like spectacularly silly way. And part of the hope I think here with environments is that if you scale these in diversity, then there's a better chance that you kind of smoothen out this like jagged intelligence. Whether that turns out to be true, I think is still an open question. but I think that's the way it's going.
Okay. So just doing a time check here. I think Sanyam had a question, and then I guess Sanyam was also the next speaker, so you can introduce yourself if you like.
No, thanks, Louis. This is like really insightful. I had a question which I think Davide might have answers to, but there's like
Let me bring him on too.
So much thoughts on, and sorry to put Davide you on the spot, but there's so much thoughts on, okay, you should like train this model in pre-training, then you go to mid-training, then RL. When you like think about environments and all these tasks we throw at the model, is there like some method to the madness that you probably wanted to like solve certain list of tasks first or certain environments and then you graduated? Because I imagine like if you have 18,000 environments or whatever, you can't just like throw everything at the model at the same time.
Yeah. Okay, the picture tends to be a little bit more messy than this in practice. Like, for example, this is something that Quen started doing a while back, but I think now it's standard practice. You actually want to inject even some of these post-training traces back into pre-training. And that helps downstream. So the whole picture is a little bit like it's whatever works. I think in practice, so there's kind of, in theory, yes, the idea of doing curriculum learning makes sense, right? You start from the easy things first, then you nail them, then you move to the medium ones, and so on and so forth. So in learning, right, you should always be aware of the bitter lesson, right? And so the more kind of human biases, I'm not saying biases in a bad term, like inductive bias, you're injecting into the process. On the one hand, you're making learning, bootstrapping easier. On the other, you are kind of constraining where search can go. So in practice, you have a lower thing. So it depends. I think this is something, we have tried even in the Llama days. And sometimes it works, sometimes it doesn't work. You normally want to kind of have some, like whenever you're undecided, it's normally good to have some sort of like random schedule to it. So for example, you can kind of sample easy examples with higher probability, and then you anneal this probability to go down as you kind of continue training. Or you can just say, fuck it. And like the fuck it approach, like kind of works actually. Like basically what it ends up being is, you start from a hard example, you're like, I can't solve it. So basically you just wasted some compute there, but you haven't constrained the model. So, depending on how much compute you have and depending, like, there isn't a kind of clear-cutting rule, I would say. But I would say that like start from nothing, because you always want a basement. And then like having some sort of like randomized schedule like that, see if it helps.
I actually have a question for you, David. I haven't seen this discussed much in literature, but there is the whole thing about like difficulty and curriculum. But I wonder, in your experience, how much of a role is like the time determination of like the sort of trajectory important? So like, for example, there's these like tasks that are like, popular on Twitter with like, okay, Claude used like, I don't know, 100 hours to do something. Obviously that in an RL would be horrible, right? In principle, because you don't want to be waiting like 100 hours to get your reward. And so do you have like some scheduling on like the kind of length of these tasks? Or is that something that is also in the bucket?
So I'm going to speculate because I haven't done something of that sort with like such a long time. I think that the problem also becomes that like in RL, ultimately you get a reward. Again, you can tweak these things, but like one of the things you got to be careful is that if you get the same reward for any trajectory, then you're going to be overweight on the short trajectories. So learning the long ones, you probably need like much higher rewards or something. I would suspect you probably would break this up into phases. Not to contradict what I just said, but I think this is just about being efficient towards your compute. And so it's probably okay to tolerate some inefficiency. But once you're going to like these extremely long horizon tasks, my suspicion is that you probably have to start from SFT again. And so you have to synthesize like a good trace. And I would synthesize it first, I think, at least to kind of get the model going, right? And then start to kind of brute force reinforcement learning. Like the problem is, if you start the brute force approach right away, if the task is too hard or too complex and you never get to something that gives you clear rewards, then you're stuck forever. One example of this was StarCraft. Like if you, for example, if you're learning chess, you can totally start from a random model, right? The random model plays itself. They both suck. And so eventually one of them is going to win. And that then kind of gives you rewards and you can kind of get the machine going, right? Not so for StarCraft. Because in StarCraft, there's so much shit going on, right? Then the sequence of action necessary to either win or lose a game is actually quite hard. And so what ends up happening is you have like the beginning of the game, a random policy will basically just kind of jiggle workers back and forth. Nobody wins, nobody loses, and you're stuck there forever. And so you have to nudge the process, but with either SFT data or reward shaping, so that you can, for example, say killing units is good, do that. Or, mining resources is good, creating units is good. And therefore the model will kind of start doing this. And then, this kind of is conducive to one of them eventually winning. Or just SFT data, just copy what this guy did and then just kind of get it going. So long sequences like this are going to be more similar to a game of StarCraft, I would say.
Yeah, that's a good point. Something I didn't mention, just to end on this, Mark, is that the environments are not just useful like in an RL loop, right? Like if you have a very good environment, you can actually use it as like a mechanism for synthetic data generation, which is again, I think the value of having like, these high fidelity, clones of like, valuable applications.
Exactly, right? So in RL, basically the price you pay is that each trace, like each episode, is less informative than an SFT example, right? That you mine from people. However, you kind of shift towards like as long as I have compute, I can generate an infinity of these. And so in the SFT regime, I'm constrained by how much data I have. And this data is produced by people, and sometimes it's very expensive. In the RL regime, I'm only constrained by compute, right? And so this is bit less on compliant because the compute curve is an exponential curve, right? Every 2 to 3 years, NVIDIA gets us like 5x the performance, right? I don't get 5x the data every 2 years. Far from it. The cost of data is always the same. It goes higher. So, right? So where do you want to be? And so that's really what it is. It's inefficient, but I have a lot of firepower.
I guess Meta has a lot of GPUs.
Yeah, okay. I mean, I will say I don't know if I'm as optimistic as you, David. I think the 5x performance every year is also sort of like becoming a bit sus from NVIDIA's case. Like Blackwell reliability, blah, blah, blah. But maybe the subject for like another talk.
But that's another.
All right, we have the one and only Sanyam. Sanyam, please take it from here. I will share your screen.
Awesome. Thank you so much. I apologize in advance for my sound. I gave my mic to my family, who I'm pretty sure have never used it. They probably sold it on eBay. So if everyone stars Unslot, TRL, and OpenEnv, I promise I'll buy a couch. Okay, that's my promise to you. I'm one of the folks who works on OpenEnv. In the intro, Mark said all of the speakers are people he respects. I'm not one of them. He let me on this stream because he likes my joke. I would quote after maybe 1 or 2 beers. So that's why I'm here. What I'm here to talk about is just give you all a walkthrough of how OpenEnv sort of brings things together and how you can bring your own environments. What's the pattern to building these environments? And I promise I won't stay between the great speakers, so I'll keep my talk quite short. But please keep the chat spamming. I already see a lot of messages coming up. I want to make like a suggestion here. One thought I have is about LLMs and models. People always assume that they want a specialized model.
So I just to double check, you just have your screen was just click to exit full screen. Was that intentional?
I was in slideshow mode. Let me see if I should share again.
Just click it again, maybe.
Is the slideshow on?
No, it's just showing click to exit full screen.
Okay, let me share my entire screen. Give me 1 second, sorry. See, guys, I clearly don't know what I'm doing. I'm sorry about that. Please complain in chat, all right? I'm bad at this. Share my screen, share my entire screen. All right, now you'll get a mirror effect with Mark in it. That's okay.
An infinite Mark, okay. Yeah, okay, this works, perfect.
Awesome. So the claim I was about to make is people assume, or it's kind of known, but just to call it out, that you assume that you want a specialized model. But what you really care about is a specialized LLM. because you don't just want a tab completion model, right? Like that is sort of helpful, but we're at the stage of Claude Code where you want these models to be really good. And from the previous two speakers, it sort of alluded to the fact that reinforcement learning can really help with this. So that's where like reinforcement learning becomes this pill where you want to inject it into LLMs so they can possibly solve any task which you can put in an environment. And Zach actually has like a really exciting talk where he'll talk about sandboxes. But the challenge with this is, presumably you have 18,000 environments like in the previous case. How do you like standardize these in a sense that we all are programmers here, right? So if you have like 5 different environments, forget 18,000, and their APIs are so different, how the heck does the model like efficiently train on this? You probably want the like compute to be utilized rather than writing all this infra, right? So that's the challenge that OpenEnv is trying to address. How do we create the standardized spec, which makes it easy for the entire community, which I think is quite similar to the spirit of GPU mode. And we want to keep everything open source where you can bring your own environments. They use the same spec. And we're like very well integrated with the best trainers like TRL and Onslaught. So everyone's life is easy, everyone is happy. And the end goal would look like something like this, where you just change the line of import at top, where you change the Docker environment or the Docker file where you're importing your environment from, and your model keeps learning. That's the goal that we're trying to march towards for the better of the community and also for better of research, if I may. So we wanted to test this theory. And funny enough, we did this like 2 days after launch. So it was quite an experience. Daniel and myself, we did a hackathon with the wonderful folks at AMD. And the models I'm quoting here, or the examples I'm quoting here, are from a hackathon trained on a single MI300X, which really impressed us. I think Daniel was really happy with the examples. Folks came up with these environments themselves. Most of them are in our GitHub repo, and they trained their agents as well using just one GPU. So from all over the place, you can see some folks solved Mario. No, they didn't exploit the bug that Davide was talking about, but that was still awesome to see. Another cool example was improvements on code writing. And if you go to the next slide, you'll see that my favorite one is on the bottom left, which was Project Pikachu, which came out of our Discord. No, I don't care about trading with RL. Who cares about money when you can solve Pikachu, right? So in theory, we did test our approach and it did work quite well. So now I want to walk you through how you can actually build these environments and how do you bring them to life. Because hopefully you're sold that this approach sort of works. But to get there, I'll do a quick recap of reinforcement learning. So to simplify things a lot, you usually have an agent which observes the world around it, chooses its action, and gets some feedback based on which hopefully it improves. And the environment is the world around the agent, which reacts to its behavior and can give it rewards. In simple code, you can assume an example of teaching a dog how to sit down. And in code, this would look like something like this, where you ask the dog to sit. And right now, okay, I'll just say it's probably my dog, right? It doesn't understand the word sit. So it just starts barking or spinning in a circle. And that makes me upset. So I scold it, which is a negative reward. And hopefully over time, it learns that it'll get a treat every time it says or it obeys sit. So that is a very simple example of reinforcement learning. But the idea is there's like a few simple things involved every time. And these are the concepts that we've built upon for the open environment spec. The 4 are you reset an episode of learning, and that begins a fresh training session. An observation is what the agent sees in the world. An action is chosen by the agent, and it's what it does. And one step in an episode of learning is just either one action or one observation being returned from the environment. So those are the 4 simple things which have been around in reinforcement learning. I'm sorry to everyone who already knew this, but we kind of settle on this spec. So to build your environment, Louis actually showed you the 2 commands. So this is kind of ridiculous that I have to show this. But when you do OpenEnv init, your name of environment, it creates a skeleton of files, which actually simplifies a lot of things, but I just want to explain them as I go. It's 5 files that you need to define, where you define these behaviors and models. So you define its action, its observation, and state data classes. And inside the environment, you expose the behaviors, which were the 3 reset, step, and state methods. Now we connect these using HTTP. So the environment talks to the client. We have to define that. And then finally, we wrap everything in a fast API server. So you never actually see HTTP. It's ridiculous. We don't like debugging tensor mismatch, so we definitely should not be debugging that. And then finally, to make this scalable, and Zach will really go in deep with this topic, we wrap everything in a Docker file. So you can actually just import a Docker file and you have a new environment. Of course, you import that from Hugging Face, and we all love Hugging Face. It's really easy to use, anything and everything on the hub. So the universal interface for any environment would sort of look like this. You define an environment and you expose these 3 methods: reset, step, and state. Now, I've been going on and on about this, so let me put a concrete example to this. And of course, I forgot the slide, but you have to also define these data structures so that things are standardized. Everything is natively Python. There's no external dependencies, but you usually define your action data class, your observation data class, and state data class. Action and observation are sort of straightforward. In state, you have to be careful about what metadata you're exposing. And I'll also call out that in state, you can cause a lot of reward hacking. So that's some place you probably want to carefully look at. Again, this is the goal we're sort of marching towards, which is having a standardized training interface so life is easy. But to put a concrete example, you can imagine the game of Connect 4. Now, I had a very sad childhood, so I actually never won a game. But for those of you who won this game, you were supposed to drop chips in a vertical column, and you can connect them horizontally or diagonally. And the first person who does that in this 2-person game wins. So an action would be Connect 4 action, which decides what column you're dropping the chip in. Observation would keep a track of what's your board state, what legal actions are allowed, and is the game finished or not. State would just keep a track of the board state, right? And you can imagine in the Docker, there's not a lot of dependencies. So you just have a NumPy array and you just wrap your fast API server to expose it. In simple logic, the reset for Connect 4 would look like, all right, empty your board, remove all the chips, set it to player 1, make sure all columns are allowed. And in any step, a user drops a chip in a column, checks if they've won. If not, the game continues. And this is what a Connect 4 environment code would look like. I just pulled this out of our GitHub. It's not formatted well. Sorry about that. But that's the simple logic for defining an environment. That's all it takes in some sense. So I would say a lot of effort goes into curating your rewards and also the questions or the prompts you're sending to your model to solve this. And the challenge that OpenEnv is trying to solve is standardizing on this approach and hopefully making everyone's life easy. So I wanted to put another inspired example for GPU mode. I'm very underqualified for this, so please excuse me if this is not right. But you can imagine a kernel sandbox conceptually where you want it to improve kernel writing would have the following methods. In reset, it just resets everything, records a baseline, probably keeps a track of observations. In a step, it receives the kernel code, maybe compiles it with certain flags. I just compile everything with default. I never even look at the flags, but I know you all are experts, so you probably would do that. It runs the benchmark, and maybe based on how better the benchmark improvements are, you give your model a certain reward. In code, that would look something like this. So your models would have kernel action, kernel observation. Your environment would be a kernel sandbox. And your fast API server would look something like that. So that's all I had to present to today. I also want to call out that we're also thinking about how to add tools to these environments, and Davide can talk a lot more about this. I would also request you all to look at our RFCs. They have a lot more thought on all of this. But we're thinking about how to expose tools both in real time and also in simulation as you train these models. One last call out I have for you all is please go to our GitHub, consider starting it, consider joining our community. Or honestly, the best thing you can do for us is just check out the project. Tell us what you think. If you don't like things, please complain to us. We'd love to make this project the best use case for you. If you were training RL models, which hopefully you are.
Sweet.
So that's all I had.
Thank you, Sonia. I guess do you have a good sense of what kinds of environments would you be particularly excited to see? What do you think are some things that people are under exploring that you'd like to see more of?
I think I'm at a different mind point now because I'm curious to learn the methods on how people are using this. For me, the cool games are always cool environments, right? Because for all of us who write code, there's this experience we had with robotics, right? Where you write code and it's holy crap, the arm is moving or whatever. It's the same for RL in the sense you have this cute little model and now it's able to play your game and hopefully play it better than you. So for me, it's that experience, but I think everyone has their own takes.
Zach has a lot of opinions on this. So Zach?
I do. In fact, I was up late working on what amounted to just a few slides, but I was going to put in a request for environments at the end. But one thing that would be really great is we're all using GPT OSS in some form or another. It comes with it doesn't come with, there's some missing tools there that would be useful. There's a browser tool and a coding container tool that they didn't open source with the model. And we could squeeze out a lot better performance if we had that same tool to reproduce results with and then develop further. So I would love to see I'd love us to do a hackathon even on the quest for the missing tools from GPT OSS.
That actually sounds pretty fun. I'd be down to join. Maybe we should talk more about this. I guess maybe Ben, do you have comments on this, or do you want to just get started with your talk?
No comments. It sounds like a really cool hackathon. Yeah, I'd definitely join in as well, but I'm pretty much ready to go with the tutorial.
I'll just say one more time for everyone asking. We will post all the materials. Don't worry about it. Just stay on GP mode. That's where the recording is. Go to OpenEnv repo. That's where we publish everything. Just enjoy the lecture. Stop worrying about materials. They'll be there.
Yeah, I mean, this lecture is already recorded, by the way. It's a YouTube link, so it's chill. All right, Ben, please take it from here.
Cool. So what I've prepared for this session is a tutorial, and it's all contained within this single GitHub repo that's called Hugging Face GPU Mode OpenEnv. And maybe in the future I'll fork it into something else, but right now I made this specifically for this presentation. But I've actually pulled some things from other places in the OpenEnv repo. So the first markdown file is on environment, and that's basically pulled from Sanyam's presentation on how to run ends, which is basically what Sanyam just presented. So I'm going to skip that, but afterwards you can come here and you can get a markdown version of that. Then I've got a markdown page deployment, which I'm going to present, and that's on how to deploy your ends to Hugging Face spaces. And then another one on scaling, which is just a tutorial on how you can scale OpenEnv environments for free. And then a final one, page 4, on training GRPO with TRL and Wordle, which is a kind of tutorial on what Lewis is going to present next. So you can start off from here and kind of get all of the resources, and that should be pretty handy. Let me go to this page 2 to start off. Okay, cool. So in this first part of the tutorial, I'm going to take you through how to deploy an OpenEnv environment on the hub. We already have a pretty good idea of what an OpenEnv environment is now. Lewis presented it first, Sanyam presented again. And in simple terms, it's a fast API web application. There's nothing really fancy to it. I'm going to go into the details and show you what that looks like. But it's a Python package managed with a nice TOML and a fast API application. It's a very familiarly structured web application. And to deploy that application, we use Hugging Face spaces as the infrastructure layer for this, right? So a lot of people kind of associate spaces as like, you know, this great kind of demo tool, and you can push your Gradio applications there, or any kind of application, and you use it for demos like image generation or text generation or whatever. But actually, under the hood, spaces have three main attributes, which are it's a server, right? Like it's a web application. It's a Git repository, like models and data sets, so you can do version control. And it's also a container registry. So you can say like Docker pull and use the URL of the space, a specific URL, this one here, and say, okay, let's pull the image of that space, and I'll run it as a container. So within OpenEnv, we can use that infrastructure without needing to build anything, right? This isn't anything specific to RL environments, but it's really advantageous. And then once we've got that container running, we can then interact with it in three ways. And so I'm going to work through that first, how we use these 3 points to access a space. So the first one is this. We just treat the space itself, the server, the application running on the space, as our RL environment. So we say to our class, our environment class, use the base URL of the space URL, and let's reset that environment, and then let's step through that environment. And in fact, we can train using this kind of interface. And I've done some benchmarking, which I'll come to in the next tutorial. And we can train up to reasonable batch sizes with a Hugging Face space like this. And we don't really need to do anything. We don't need to pay to deploy it on a upgraded system. This is just like the free tier space, and it will work on most examples. So what kind of endpoints does this application have? It has a WebSocket endpoint, which we recently implemented, and I'll come to why we implemented that and how that's useful for the community. But it also has HTTP endpoints, which you can use to reset and step through the environment. Okay. The other point that we can interact with a space is that it's a repository, right? So we can pip install the code from that repository, which in the context of an environment is very useful because we can install the client code of our environment in our client side. So we can say like pip install space URL and get client code, and we can say pip install we can say Docker run and then use the container image. We've got the same thing from two places. And then the last point is this Docker registry, which I already kind of came over, where we can say, okay, let's pull this space as a container and then let's run it, or we can just do like this. And so what that means if you're building environments is that you only have to manage one location, right? And here's all of that kind of summarized. So you could do, as I said, you could interact with it as a running space. You could run the container like in another terminal and then interact with that running container locally. Or like a kind of just an abstraction of that, you can just say from hub and use the repo ID, and it will pull that container and then run it, and you can interact with it. Or in fact, you can say, I don't have Docker available, so pull that Python code and run it using Unicorn and run the application locally, and then let me interact with it like that. And so we've got these 4 interfaces to the same space, which we can use to run in different ways. And I'm going to work through those now. So the first one is just to use the Python code itself for the fast API application, kind of the most obvious. So we can clone the repo and then sync the Python package. and then run the server. This like uses a script, sorry, but we could also just use the unicorn command. And then we can, or we could refer to the project itself and run the script like that. And then we can interact with our unicorn server and like define the host and the ports and run the server. Or moving on, we can run the Docker container and use the same example. We can pull the container and then, we can clone the repo and then make changes to it and then build the Docker container as well. And inside the OpenEnv CLI, we've got like a convenience tool, OpenEnv build, that does that for us. But it's essentially just wrapping Docker build, so we can also do the same there. And then we can run these containers and, as I said before, connect with them from Python in the same kind of way. So what does it look like from the CLI? So as we showed before, you can do this OpenEnv init and you can create the skeleton, and then you can push that straight to the hub, which I'll come back to in a second as a little demo. And then you can configure that environment mainly with environment variables to say like how many workers do you want to use and whether you want to use concurrent environments, which I'll come to in the next section. So feel free to kind of drop in any interruptions if you like. I'm just going to set this up so it's a little bit easier to see.
Yes, I had a couple of questions. Like basically, so I know you mentioned at some point, like, oh, if you don't have like Docker, you can use UV. But like, how does this work? Like, I mean, presumably most environments aren't written in Python. Like, if you're a Pokemon, you're written in like whatever that was written in. Then you have like some shim in Python. So, like, could you speak to how like basically native code gets deployed in environments on the hub?
Yeah. So when the environment is outside of Python, you need to use a container to define the code outside of Python and do dependency management, basically. So if you say like, if you want to run the unicorn application, the Python application, you need to manage the dependencies outside of Python, and we'll do that with Docker. That's basically, yeah.
I see. Just and I know this may be a pedantic question, but just because you have cost there. So the cost basically, it's like, is it like paid for by the people hosting the environment, or is it paid for by the people that are pulling the environment? How does this work if people are having like multiple rollouts where they're doing multiple parallel evals?
Yeah, so in the example I showed you where like this kind of example where you interact with the space itself, right? Like the environment host would pay for that compute. And so in most cases, like if you're publishing an environment, you would probably want to do that free and just let people try it out and kind of understand the environment that you use to maybe learn from it. And then they could pull that environment and run it for free. Because of how Spaces works, like, let me just maybe show you, like, you can just duplicate Spaces, so they're kind of like super easy to just pull over to your own.
I see. Like running locally is something you want people to do. Like you want them to discover things and then like, I see.
Totally. So yeah, I expect most people will like come here and like try it out and learn from it, maybe duplicate it if they want to make changes and share it. But in most cases, we expect people to kind of to run this locally.
Got it. Okay.
Cool. So yeah, okay. So I shared this little demo, and we've kind of seen this a little bit already, but let me just work through it. So you basically just do OpenEnv init, which looks like this, and it's a simple command line. It just needs to know what the name of your environment is going to be. So let's call it GPU mode. And so we basically, I'm in the right place. Okay, sorry.
Sorry, I just had a quick add to what Ben answered about Mark's question. For like most of these game environments and things like that, you can imagine you sort of building adapters or wrappers, just like add on to the spec. But our goal for like, hopefully this year is we'll bring like environments on the ground up. So we'll see them like being less clunky. And the other thing I want to call out is like most of these are for reinforcement learning training. So that will go in a lot more depth, but the CPU cost of running an environment compared to like the GPU involved in training is like really fractional. So you can imagine like you probably would not mind hosting these on your server. Sorry to interrupt your flow, Ben.
No worries. It was actually extremely helpful. Gave me a chance to get this back in line. So yeah, okay. As I was showing you, this is just how you initialize an environment. So, and I just want to kind of work through that. So let's say I'm going to create a new environment called GPU mode. So I just say OpenEnv init GPU mode, and it creates that for me, and it tells me that there's this new file called OpenEnv mode. So let's go and have a look at that. And if you look over here in like the file explorer, this is what it looks like, and this is a skeleton. So it comes out of the box. So if you're looking on the right pane here, and it comes out of the box with this README that has some metadata, which makes it discoverable on the hub, basically, but also gives you like the templates. And you'll notice that we've like sedded the entire skeleton so that it's already pre-constructed for you with the name that you chose, which in my case was GPU mode. And it gives you all of these examples of how you do it. So out of the box, you have like a self-contained, fully documented env that is also interoperable and standardized and uses OpenEnv. It comes with this PyProject TOML, which installs all the like the base dependencies that you need, and then gives some like recommendations and gets that running. And then it has the client code itself, which Sanyam already kind of unpacked and went into detail on. And that's all that, right? So then let's just change into that. Probably don't want to go too far into this because we want to go into the some other things after that, but we can then basically just like run this env like this locally. Sorry, that port's already in use. So yeah, okay, that's it running locally now. And then if we go to our like Python interpreter, I think I have that here. So okay, if I did that, I think it wouldn't work because that's not deployed. But if I copy the URL out of here, then I can just say, okay, run on here. Yeah, okay, and then it's like step through, and there's the reward, and then another reward. And that's this OpenEnv environment running here. And then let me just now go back to my terminal, close that down, and do OpenEnv push. Hopefully I'm in the right directory. I was, yeah. Cool. So then that's now pushed it to the hub. And if I go over here, I open the browser, you see that I've got this space running here, OpenEnv. And then I can just like test out the env here. And this is just a skeleton env. It just like echoes back whatever you ask it. So it's just echoed back hello. But if the env was like more complicated, or let's say it was like Sudoku or text arena or even browser control, you could try that out and kind of get a sense of how that environment works and what the model was doing for this use case, like in the space. And then you would be able to, as I show you, go here and kind of duplicate it, embed this space, but you could also run locally, and then you'll see this Docker run command, which is the same Docker run command from the docs. I think this should just drop in. Yeah, and so then now what you'll see it's doing is that it's running the same container image from the space inside, like locally, but this time via Docker instead of the Python server, the fast API application. So that's it. Let me see if I can also just interact with that like that, just to kind of complete the loop. I think that one should work. Yeah. So now you've got like the same application running in the space, which you can also use. Okay, so that's the deployment side of it. The next little tutorial I've got is how you scale these environments. So I'll just move over to that. Any questions while I'm moving across?
Yeah, I had two. The first one was like, what's the like UI framework for rendering stuff? Is this like a Grad.io like based inspiration, or is it like when you're in the browser?
This one here, it isn't
Yeah.
actually. This is a very simple, just index.html with some plain.
I see. Okay,
yeah.
supervision.
We consider getting Gradio involved, but in most cases, a lot of people are kind of hacking these interfaces for their various environments, and so we didn't see the benefit in standardizing the UI too soon because, there's a lot of experimentation going on there. Like, for example, around like a Connect 4 game or a Wordle game, like how do you visualize those games so you can understand what's going on? When I was running training loops and like debugging processes, I found this UI like really powerful because I could create on the side like a little rendering of Wordle, for example, to get a sense of what the model was actually working through in those like first few steps.
So speaking of rendering, like this would work for like real-time games as well. Like, I mean,
yeah, I experimented with Pong, and I don't think this UI would work in real-time games, right? Like, that's where I think we would want to move on to a fully fledged UI.
I see. Okay, got it.
Cool. Okay. So scaling. So I'm just going to give you a kind of community idea of how you would scale OpenEnv, and Zach is going to come back with a kind of big boy scaling, and this is sort of like hacker scaling and how we get to like greater than 1 containers and these kind of things, so that you can get to like sort of humble origins training runs and try to understand RL in the early days, as it were. So there are 3 main ways to scale. The provider, which is an integrated class in OpenEnv, but I'll explain. WebSockets, which are a way of having sessions, like multiple sessions on a single container running concurrently, and then scaling the services themselves, right? Horizontal scaling. And I took through a series of experiments to like basically see how far I could push each type of infrastructure. So starting from Hugging Face spaces, like free tier, to paid servers on Hugging Face, to compute instances, and then multiple compute instances with load balancing. And I kind of worked up those first few steps, like up to, let's say, GPU middle class, and how you would scale. So the first way and the easiest way, which most people will come to straight away, is to use a provider. And at the moment, there are 3 providers implemented in Uvicorn, and there's a Kubernetes one on the way. But we could add more providers for various different container runtimes, right? So the first is a Docker provider, which uses your local Docker runtime. It's the default one, and it's the most straightforward. The second is a Uvicorn provider, which combines UV and Uvicorn to run Python-only code inside for your environment. The third is a Docker Swarm provider, which uses the Docker Swarm runtime so that you can have concurrent environments for your concurrent containers for your environment. And so with these, you can run containers on your laptop pretty easily and get them to concurrent environments. And so if you're doing, let's say, like evaluation or inference workloads using an environment, you can get pretty far with these Swarm providers. And if you were going to a single instance with multiple GPUs, you could use the Swarm provider and scale pretty far there. But in fact, we can already get quite far on one container with WebSockets. So this was actually pretty much a purely community implemented feature, so where we use, as well as HTTP endpoints, we use a WebSockets endpoint. And if you're not familiar with WebSockets, they're a persistent, long-running connection from client to server. So a HTTP request will send a message from client to server and back, and the client will track the state, and the server may remain stateless. And in that environment, in that situation, your environment your container has a single environment that maintains the state. That's kind of ideal for situations like a coding environment or a file manipulation environment, where you want that to be sandboxed, right? But in a situation where you don't necessarily want it to be sandboxed, you want to get concurrent sessions running on a single container, then WebSockets become really advantageous. And that's where the community kind of came in to implement this, was because a lot of people were using environments like Wordle, Sudoku, 2048, these kind of things, and they were deploying single containers in order to do it, which became really resource intensive quite quickly. And so with WebSockets, we can have, say, parallel sessions running inside a single container. And basically it looks like this, where we instantiate a new env on a single container, and every single time we instantiate an env, we get a new session. And so if that session becomes idle, as let's say the GPU performs inference, then it doesn't lock up the container and it doesn't continue to consume any memory. So by taking this, and just to show you that the implementation of that, this is what it looks like, that every single time we start a new session, we just create a new environment. So you have this connection between sessions and environments. And the takeaway from this is that instead of having a single container for every running env, like HTTP, we have as many sessions as we need for the memory and compute resources of the process within a single container. Okay. Okay, I'm going to come back to the experiments on that. Feel free to ask me any questions again. How do we scale a single container? Well, that we can do with workers. So we can use Unicorn to create, to run multiple workers and to have the application running across processes. We can use asynchronous clients as well, so that we don't lock up the server when we're using the GPU, for example. And we can do the same and pass those to to Docker. So the other element to say is that, which I've just kind of skipped over, was that as I said, some environments, like a coding environment, they want to be sandboxed and they're ideal to be sandboxed. And so we can pass an environment variable to those environments that says max concurrent ends is 1. And we say we don't want to run multiple sessions in a single container. And actually, when we build the environment, we can define that within our skeleton and say, max concurrent ends is never greater than 1. This is a sandboxed environment. Okay. So that's how you deploy it, and that's how we kind of squeeze the most out of these single containers. We tried it on Hugging Face, and we get up to concurrent batch sizes with something like Text Arena, which is Wordle or Sudoku, and other text-based games. We can get up to concurrent batch sizes of 128. If we use a paid space, we can get up to concurrent batch sizes of 512, which is way beyond the kind of comparably budgeted GPU. So there should be a lot of room for people to try out spaces and, let's say, like just set up quite simple experiments. And even the CPU upgrade space is 3 cents an hour. So we're not really talking about high investments here. And so what I experimented with was how far we could push these ends to find these numbers, basically. And what we found, this is the takeaway kind of image. What we found was that at this number of around 512, we got to the capacity of a single 48-core CPU. And then by using a load balancer, we could take that up to 16,000 concurrent requests. And Zach will show you examples going kind of like even beyond that. And we did that using a load balancer. So I set it up with Slurm and a Envoy load balancer. But actually, you could deploy this on cloud providers using something like GCP's Cloud Run or any kind of managed load balancing service, and you'd be able to deploy these environments quite easily. And the experiments that we run, let me just zoom in a bit. We found that these local Docker containers were able to get quite a lot of concurrent requests out of them. We could get up to 2,000 concurrent requests running on 8 cores. And with 2 nodes, we could get up to 16,000 concurrent requests. So that was our kind of, I'll just work through the findings now of this little experiment. And the first finding was that you can have like really high concurrent requests running on quite small devices because we're using the WebSockets and concurrent sessions. So if you're doing workloads like evaluation or inference, these can scale pretty far, and you don't necessarily need to use a different environment tool for local or training. We found that the sweet spot number for Hugging Face spaces was around 128 concurrent requests, and we can go a little bit beyond that, but then we hit the Hugging Face Hub rate limit, in fact, so it's not necessarily the compute. We can get beyond that rate limit with premium hub subscriptions like Pro. We can get a greater rate limit, but in most cases, we probably don't need that. The other finding was that, yeah, the multi-node scaling works and is pretty easy to set up and get to these high concurrent requests, which are really informed by the resource consumption of our environment. And this is what how they scale at each point. So the first one is the spaces, where around 128 they collapse, and that's just because they're getting rate limited essentially. And then these numbers of 512, the single core starts to drop away as it times out basically. And that's where we use the Envoy load balancer to go to greater than 1. So I'd recommend that you could take a look at this experiment. But if you want to try it out on your own workload, you can run these experiments. It's in a project called OpenEnv scaling, and you can run these tests on your own environment and kind of see to what scales you can get. But in most cases, the takeaway is that OpenEnv is an ideal tool for like community users, but also people that want to scale beyond that. So that's the takeaway. Cool. Are there any questions?
No, yeah, I think this was quite clear. Thank you so much, Ben. I really appreciated like these experiments. These are quite nice. I guess like then like the sort of interesting stuff might also be like sort of end-to-end profiling of like bottlenecks, like basically where do the bottlenecks show up, like between like just like scaling up well, maybe not, because like I feel like this is all just like very embarrassingly parallel, so it's like quite easy to scale and understand the performance characteristic of like deploying large scale environments, right? So it's not something that I expect would have too many performance foot guns when doing RL training.
No, the technology is familiar, right? They're fast API web applications, and you're using horizontal scaling, and so cloud providers are kind of full of like services and tools to scale these environments, and so everyone will have a preference. What I think is really distinctive to an RL environment compared to like a web application is the reproducibility and like the relationship that the environment has with the data set and the model itself. And so that's kind of the next steps for environments, really, of like how we connect a model that's published on the hub to its environment in the way that we already connect it to its data set, so that people can understand that environment, read the paper, and then kind of take away those findings.
Very cool. Well, thank you, Ben. I guess we have 3 more talks, everyone. I think the next speaker is going to be Lewis. So let me bring him on.
All right. Cool.
Do you want to share your screen?
Yeah, can you see this VS Code?
Yes.
And I apologize for the audio. I am in a dingy office, so I'll try my best. So what I thought would be good to kind of build on top of what Ben showed is like, okay, we've seen now how these environments are like deployed on Hugging Face Hub and how you can interact with them. But I thought it'd be useful to sort of show like just one example of then how you put this in the RL loop. And I thought it'd be fun to just take again a fairly simple example, which is Wordle. And you know, Wordle is a simple game, but it is a very good example of the type of game where RL helps, because it's got this kind of sequential decision making, where the kind of decisions that the model has to learn how to make depend on the previous state. So, as Ben showed, you can go to like the Hugging Face Hub, and you can go to the OpenEnv. Oops, I can't spell. The OpenEnv organization, and here we have a bunch of like curated environments that have been contributed by us members of the community. And basically in here, there's a collection of these various environments. And so if you're looking to sort of get started on using OpenEnv in an RL loop, you can take some of these. And the one that I wanted to look at was from Ben, where he has a Wordle example. So, a typical thing, the demo gods are against me today. So, if you go to a space at an end and it's broken for some reason, then what you can do is duplicate that space. And then this gives you, as Ben explained, kind of like full control over that environment. And so I already did do the duplication myself. And so here I can find some point, the space I made. Let's go here. I guess it's this one. Okay, I have to find the space, but basically it's like this, and then we can either run this locally, but what I'm going to do is I'm just going to make a WebSocket connection to it directly to the hub. So we instantiate our environment, and in Wordle, the idea is you provide some initial guess for the word. We're going to reset the state of the environment, and then we're just going to take a single step with this action, which is going to be the guess. So in this particular environment, we make a guess, and we get this kind of result, which has a bunch of information. It has an observation, which we talked about. It's like the thing that the environment gives back from given action. And in that observation, we have like the reward that was given, and we also have like something about the sort of the history of the state in terms of the messages and some other things. So if we just pick out, for example, the current state, this is typically what is getting, or what is going to be provided to the environment every step. And you've got kind of like the prompt that we're going to give to the language model, and we're going to tell it that, okay, you get feedback, like, green if the letter's in the right place, yellow if it's in the word but in the wrong place, and just and so you can see here, I gave it the guess crane, and it told me that, okay, the letter C is in the word but in the wrong position. And the idea is we're going to teach them all to kind of like iteratively get better at making these guesses. And so if I take another step, then now you can see that it's essentially concatenated the previous guess. So here was my initial one, and now I've got a few guesses left, and now it's giving me this. From this, I've learned that, okay, the letter C is in the word, letter T is in the word. We could go on and so on. So the way this works in TRL, and it's I think pretty similar in Unsloth, is that we're first going to instantiate the model we want to use. To run this kind of like in a simple way, we can take any sort of small quen model or whatever your favorite model is. In general, if you're going to do RL properly, you would probably want to pick a model that's like better suited for the task you're trying to do. But this is good for demo purposes. And the first thing we're going to do is define kind of like a fairly detailed system prompt, just to sort of like tell the model, like, some of these models maybe don't know about the game Wordle, and so we need to kind of give it some information about the rules, and in particular how we want it to respond at each step. And then there are some like kind of tips on like the strategy for doing this, and then a kind of example of what the input looks like. And these things, if we waited, as like Daniel explained, with RL, we can just wait and have patience and just wait a long time, and the model will eventually learn some of these like rules about like strategies and stuff. Since we're working with small models, it just helps a bit if you craft like a good system prompt just to get it kind of conditioned in the right place. So let's pick system prompt, And now the next thing to do is to define what we call like a rollout function. So what this rollout function is going to do is we're going to have like a bunch of prompts, and each prompt you can basically think of as like, you know, a simulation of like the Wordle game. So what we're going to do is we're going to route these prompts to different sessions of the Wordle environment, and the model is going to have a shot at making a guess, and then we're going to get the response on the current state, and then we're going to use the resulting rewards to then do the optimization, and then in the next training step, we're now going to basically have the history of these guesses, and then we're going to update and so on. So there's like some things that you have to specify, like for example, like the kind of things that you need to forward to the trainer. These depend on the training framework, but OpenEnv is like agnostic to that. So the idea is that OpenEnv exposes a kind of standardized schema or an API, and then it's up to the training framework to then figure out, okay, how do I integrate that API then into you know, the training updates. So as I explained before, you basically just iterate over the prompts in your batch. You generate an episode. So in this case, we've got like 6 turns. So the model has basically 6 attempts to kind of guess the final solution. And then based on that, we're going to get some information, you know, to sort of whether the model is correct, guessing the final answer. And we give it some like kind of partial rewards because we want to kind of incentivize it to recognize that, for example, if there's a letter in the correct position, that it should not just randomly change it. And that's what, for example, the green reward is doing, whereas the yellow reward is incentivizing the model to essentially, if it recognizes that it got a letter that's correct in the word, but it's in the wrong place. So it should then learn to eventually, you know, reuse that letter in a different location. And this is something that, like, I think Daniel alluded to a bit, but this idea of like how you shape your rewards is actually quite important, because it's not just a question like, you know, if we just told the model like what is correct or not, just based on whether it solved the episode, this would probably still work, but you would have to wait like considerably longer in training versus providing it with like this kind of like partial reward around, you know, okay, you already know that if you got a green a letter in the correct position, then you should just keep it. So these are kind of decisions that one makes as a model trainer. Is a bit like sort of how much shaping of the reward you want to provide, and that depends on the task difficulty and, you know, the model. So we're going to define that rollout step, and then this is something that we do in TRL to basically just define like a single rollout. I'm not going to go into it; it's just a bunch of sort of like, you know, code, but roughly speaking, you want to just figure out, okay, given a single prompt, how do I then go all the way from feeding that to the environment and then collecting the rewards? And so here, we're going to take some number of turns, and then for each turn, we're going to build up essentially the state of the messages. We convert this into like a prompt that we can then generate rollouts from. And basically, we compute our rollout. So these are going to basically be the guesses at every step. We extract the guess with the parser, and then we do the part with OpenEnv, where now we've got a guess, we feed it to the environment, we get a result, and from that result, we can extract observations, the score, and also any other types of reward. So this is like a kind of standard, like a little bit of logic that typically one includes to sort of specify precisely how the rewards are obtained from the environment. But in general, it's just a little bit of workflow that, you know, nowadays Claude is very good at. So we define this rollout function. There are some helper functions, but we don't need to look at them. And as I mentioned before, now we just sort of define these reward functions. So we're going to tell the model that it gets a reward if it gets the correct, you know, final word. And we're going to give it these like partial rewards for like basically getting letters in the right place, and also for getting letters in that are part of the word. So we do this. And the final step is to kind of define a data set, which in this case is just a very simple prompts, like play Wordle like an expert. And then we're going to define now the kind of like hyperparameters that are going to drive the training. And I won't go into too much detail, but there's just the standard things that you typically get with reinforcement learning. So you typically want to define the batch size, your learning rate, how many epochs from the data set. Then you want to define like the kind of size of the group for GRPO, how long your rollout's going to be. Because it's Wordle and, you know, the words that each gets will only need 5 letters. We don't need to make tokens. And, you know, this is all running with like VLN in the backend, so it's here, but this is like, you know, pretty standard stuff if you've done RL. So we set that up. We instantiate our trainer. So we basically provide the model, the reward functions, the data set, and the logic for how we do these rollouts. And this is now going to basically load the model and kind of get everything set up for training. Bunch of warnings, whatever, doesn't matter. Let's get to the meat of it. And then once that's ready, we can then hit train. And so this will take maybe 10 seconds. There we go. Maybe while this is going, if there's any questions, Mark, I'd be happy to answer them.
No, I think I'm just watching. No questions on my end.
Okay. Okay, cool. So this is now kicked off training with this environment. And one of the kind of things that we're building at Hugging Face is like kind of local first, fully like open source project for experiment tracking. This is called Trackio. And what this will do in TRL is it will then, you know, you could run this locally and then you could just inspect the logs locally, but it will also create a space for you. So if I go to the space, now this space is collecting all the metrics that are exposed by the TRL trainer. And so we get, you know, all the things that are useful for like kind of diagnosing an RL run, the entropy, kind of fractional, like distribution of the rewards, the variance, all those kind of things. And yeah, basically you will be able to then, you know, monitor the reward of training over time. And I would say that's probably it. I think I don't need to go into too much more detail. This is just a very quick example of like how you can sort of interface OpenEnv into a specific training program.
So Lewis, a question I have here is like, at least like for your own personal experiments, like I think sort of spinning up something on a Hugging Face space like might make sense if you're doing like a 1 GPU sort of RL experiment. And so like at least for your own research, just because you've covered spectrum from poor to rich throughout your career, like what's sort of the sweet spot at which you run experiments where you're like, I just want to see if this thing works or not? Are you often running on a single GPU, a node, more? Could you sort of speak to us a bit about how you make these decisions?
Yeah, so I guess there's like two axes. One is like at what scale of compute do you run just your training? Like, is it like just general principles of like how do you start your training runs? And in that context, the general like, again, it depends on if you're doing SFT or RL, but generally trying to get the simplest possible like sort of.
Yeah, I'm mostly referring to RL here. Like basically,
Yeah. So in the RL context, and particularly with like environments, like at Hugging Face we use Slurm. So we have our own cluster, and we use Slurm to kind of basically like automate a lot of the scheduling of the different pieces that go into the RL. So things that we have to consider are like the VLN servers. You want to create essentially nodes for training and doing optimization, and then you need nodes for the environments. And they live on different devices, right? So obviously for training and inference, you want GPUs, but for most of these environments, you want like lots of GPUs. And Slurm is very good at basically just creating very large partitions of these environments, which then you can directly interface into your training loop. So I would say in like a real world case, that's kind of like but to start with, you typically want to simplify the problem as much as you can. And so in that context, most of what I'm doing is typically on like one node. So 8 GPUs is like kind of sweet spot for like small model training, and then with like one environment. It's kind of like you're just trying to check, like, are you getting signal? Do things work? Does the reward go up? But then when you want to do it properly, you then do it at scale. Typically, at least for us at Coinbase, we're talking like roughly say 10 nodes of GPUs, let's say 80 GPUs for like sort of mid-scale, small-scale run, and then some number of environments.
And then, so for your training code, are you using like sort of like some of the nano work that Noman has been working on? Like, is it like more like Torch Titan based? Is it like PyTorch? Is it deep speed? What's worked well for you?
Yeah, so that's a really good question. As you may know, the space of post-training frameworks has exploded. So there's like, I think 20 different frameworks, and they all have like, say, strengths and weaknesses. In the context of RL, there's actually, like, I would say, a broad spectrum of like which frameworks are most suitable for which thing. So, for example, like Unsloth is extremely well suited in like the resource constraint setting. Like, Daniel has done amazing work getting LoRa and QLoRa and like all these different tricks to work in that way. At the other extreme, if you're trying to like train like, let's say, 100 billion parameter model with RL, you're going to need some like pretty dedicated like framework for that. And in that space, there's not too many options. There's PrimeRL from Prime Intellect. There's a few Chinese labs with open source things like Slime. That's from I think it was ZAI. And then there's like this Miles framework and TorchForge. So these are like kind of like the heavy duty stuff. And in those cases, what you trade, like if you look at the extreme of like Unsloth, these other ones, you trade the ability to just do stuff on a notebook. Or like, okay, now I have to start thinking about Docker and Kubernetes and like all those kind of, let's say, slightly annoying things. So, and TRL is not really, it's like, it can kind of scale to a certain range, but it's like, it's not really built for like these like, very, very large
Okay, got it. Well, thank you so much, Louis. I guess our next speaker, if I remember correctly, was actually Daniel. Let me pull him up.
Hello. Well, actually, I had questions, actually.
Yes, go for it.
I was actually going to say, like, I actually recommend people to use TRL and, like, even for large training runs, like, it generally works pretty well. For, like, a previous slide for track.io, is it, like, does it go inside the Colab notebook? Like, does it just run inside of it?
Yeah. So basically, track.io, Trackio, I don't know how you pronounce it. You can run it in a bunch of ways. So you can be purely local. So if you have like a Python training script, it will then spawn locally, like an endpoint. You can then interface with the dashboard, the radio basically running locally. Or if you're running a Colab notebook, it will then, you can create the dashboard in the notebook for you. So instead of like having to go up into spaces, it's there. Or like for me personally, the advantage of using like spaces is that then you've got persistence. So like if I accidentally delete the logs locally, at least I can see this kind of on the hub. And the advantage of the space as well is like for sharing with my collaborators, right? Like it's easier to say, hey, here's a link to a space. Look at this experiment, and you can group them. You can fill some lines.
Yeah, that's pretty cool. Like because I was like, I didn't actually know before when I was using Track.io, like, it can actually render inside of notebooks. And I was like, oh, okay, I'm shocked. Like, you don't need to like access some other like, logging system. It's just inside of the notebook itself. And, you can see the plots move in the notebook. And I was like, oh, okay, this is pretty cool. Okay, I guess I will go to, I guess I was going to just do a repeat of Lewis's one, like, showcasing how you can do a notebook. But I think I'll focus a bit more on the reward hacking side of things. How to like actually, like, for example, so Unsloth is built on top of TRL, and we add a few extra things, how to do data preparation, how to make it a little bit more efficient and stuff like that. So I'll probably showcase that. Wait, I'll share my screen.
I think
Oh wait, no,
And Lewis, if you like, we can just keep you then on the this visible. I'll go away here. Then Daniel, want to share your screen?
okay, yes, I will. Can you guys see that, the open environments page?
No. Yes.
Oh, okay. Yeah. So like, definitely go to, you can just type in Google OpenEnv, and you'll get to like this GitHub page. Definitely star the package. There's a lot of environments that, people can, utilize. Yeah, there's like so many. But, if you scroll a bit down, there's like, how to use open environments. And then there's like some examples. And then we'll be using the Unsoft Colab notebook. There's a TRL version and other people's, partner notebooks. But if you click on Unsoft's Colab notebook, so this is what we offer to people. And this actually can run directly inside of a Colab T4, which you can utilize for free. And so the main goal for this notebook is how to do the 2048 game using reinforcement learning. So I was talking about this previously. At the very beginning phase for reinforcement learning, the model doesn't really know how to play 2048. And so the goal is, how do we make reinforcement learning force it to play the 2048 game by generating a strategy. And so that's kind of the process for the notebook. This notebook will run directly, and it should be for free for people to use. I think people get 3 hours of free compute from Google Colab per day or something. If you do run out of the credits, you can utilize Kaggle, which has 30 hours for free per week. Hugging Face, also definitely check that out. They also have some notebooks and some compute from Hugging Face jobs, for example. So try that out as well. But for installation, we have to install some stuff. It looks a bit complicated, but it's actually just pip install unsoft. And we're also going to be using track.io as well to show the notebook, show the training loss inside. And you have to get the open environments, GitHub repo, and then we'll be actually fine-tuning GPDOSS. Zach was talking about GPDOSS. GPDOSS is a great model to fine-tune. It's already a reasoning model. So, many people keep asking me, why would you train a reasoning model, to do more reasoning? What's the point? So the biggest problem is, for reasoning models, they are very good for generic tasks. But if you want to specialize them into one specific task, for example, just to generate a strategy for 2048, or to create, to do weather simulation, or to, do stock trading, generate strategies to trade stocks, for example. You don't want the model to have generic capability. You want to somehow train, do RL or fine tune the model to just focus on this one specific task. And so this is the whole purpose of the notebook, to showcase that if you want to do RL to solve 2048, it's actually not that complicated. And so, we do a lot of optimizations on Unsoft side to reduce memory usage. For example, we will be using 4-bit. This is dynamic 4-bit, so you cannot quantize every single layer down to 4-bit because you will damage the model. So some important layers are left in higher precision, 8-bit or 16-bit. We also, for example, offload the embeddings to RAM to save even more VRAM. I think this saves 1 to 2 GB of VRAM. And as Lewis was talking about, we'll be using LoRa. So what LoRa does is, you don't need to train the entire model. You essentially add 1% of extra weights to the model, and you only need to train these extra weights. And interestingly enough, this actually works. And so the main reason why this works is, models, you don't need to train every single parameter if it's some specific task. If you want to specialize the model, you only need to select a few parameters of the model to update. And this is the LoRa weights. You don't need to update the entire model. So, once you import Unsoft and stuff like that, you will see some stuff like this. But then, this is to add the LoRa. Yes.
There's a question, Daniel. So I think historically, with LoRa and then QLoRa, people were okay, it probably works for SFT, but maybe not for RL. And I think one of the intuitions there was that because you've got this small adapter, maybe you're not going to get the full capacity to actually learn the kind of meaningful signals you want. And so the question I have for you is, we know from now this work by thinking machines that LoRa doesn't really work for RL. but you use QLoRa a lot, and have you also had success doing this across a range of tasks? Like, does the quantization affect these in any meaningful way?
Yeah, that's a great question. Yes, so Thinking Machines released a blog post, LoRa Regret. We actually collaborated with them coincidentally on that. So we actually had a section inside of the blog post showcasing how you can set good parameters. For example, in the blog post, they mentioned how you need to select good LoRa alpha. You need to target all of the parameters. Like you're not just supposed to do LoRa on the attention matrix, but you must do LoRa also on the MLP. You need to do LoRa on everything and select some other good parameters. But I think, so for QLoRa, what QLoRa is, and different from LoRa is you leave the model in 16-bit. So you don't do any quantization. QLoRa is you quantize the model back to 4-bit to essentially, reduce memory usage and, can fit it on, much less memory, and use like consumer GPUs, for example. Or you can fit like ginormous models that don't even fit on like, GPUs, and you can like use 4-bit. So the trick for QLoRa is once you finish the QLoRa process, you do not merge the model back into the 4-bit weights. You only take the LoRa weights and then you merge it back to the 16-bit original model. And so that's what we found to work very well. You should not actually, so you should do the training process in QLoRa, but then you discard the QLoRa directly. You discard the 4-bit model, and then you take the LoRa weights that you learned via QLoRa, and then you merge it to the 16-bit. And so in Unsoft, we actually do this automatically. So we don't upcast the 4-bit to 16-bit and then we merge it back. We actually download the original 16-bit version and we put it back. And so that's what we found to work very well. Yeah.
Very cool. And my final question is, there's a lot of discussion about this like trainer inference mismatch, right? So the kind of precision that the model is for generation versus the precision you use for the optimization. When you do QLoRa with like Unsoft, do you treat everything the same? So like the inference is in like with the LoRa with the adapter, or is it like, you do the merging for the inference and then you switch back to the LoRa for the training?
That is a great question. So what we found to work very well with the lowest error rate is you need to, so we do in Unsoft, what we do is we do something called weight sharing, where we launch a VLLM instance, and then we essentially suck the weights out of VLLM into the Unsoft land. And then essentially what we do is we can cut memory usage by 2. So previously in the olden days, when you have inference and training, so reinforcement learning, you need to have inference and training. You need to essentially double the weights that you have to have because, the training side is like, updating, the inference side is also, you have to like sync the inference and training side. You can use like, for example, standby or like, VLLM sleep feature to like make this a bit more efficient. And we also like, for example, have that. But what we found to work very well is if you are doing QLoRa, the VLLM weights must also be in QLoRa. If you do like LoRa, for example, then yes, you will get divergence. And so during the training phase, everything has to be the same precision, right? If you do QLoRa for training, inference must also be QLoRa. However, when you do inference, so when you finish the RL process, you do not need to do QLoRa. You can just take the LoRa weights and merge it back to the original 16-bit model, or even just do LoRa in VLLM. So we actually found that to work very well. So yeah, does that kind of answer your question?
Really cool. Yeah, perfect. Awesome. That's really interesting.
Yeah. But yeah, we also, to like continue, like, for example, like gradient checkpointing, definitely use this method. So we offload gradients to RAM asynchronously, and then we bring it back. So we introduced this, like, I think like 2 years ago or something in September 2024. And I think like, many packages utilize this now. It's very, very useful. You can increase context lengths to like very, very long. I think GPDOSS is like 500K context lengths by using this methodology. So this is pretty useful. But yeah, like once you launch an open environments, OpenEnv has like many environments, and they're all open source. And, for example, we'll be using the 2048 environment from OpenEnv. And to launch this inside of a Colab, you actually have to do a little bit of, you have to do a bit of tricks to make it work. But you can launch the open environment, 2048 inside of this Colab, workspace. And then, for example, if you try the 2048 game, try the 2048 game, you can see the state, right? This is the state. What are the legal actions? And so this is kind of like what OpenEnv provides. And we don't just want to look at the state because it kind of looks a bit, we want to somehow render this. And so we made some function to like somehow render it into like a nicer format. And then we actually called a language model to generate some ASCII art for this. So for example, the current board looks kind of like this. If we do some actions, for example, the board will update. So OpenEnv actually allows you to execute actions for the current environment. And so, for example, this action, we do the action 0 and it does something. And then we do the action 1, we do the action 2, and we do the action 3. So one of the questions for reinforcement learning is, what does action 0, 1, 2, and 3 actually mean? And so like, we essentially force the language model to learn what these actions actually are doing. So we don't actually tell the language model, oh, okay, action 0 is moving up or something, right? Action 3 in this case is moving left for the 2048 game. You don't actually have to tell the language model that, what these actions actually mean. And so during the process of RL, the model will essentially learn what 0, 1, 2, and 3 actually are, these types of actions. And so we also, in OpenEnv, we also get legal actions. So for example, what is the next actual action that you can actually take? So some actions are forbidden. For example, in chess, for example, you can't do some actions, for example. So OpenEnv actually limits these. And so actually for the environment setup, there is some code to like call OpenSphere from OpenEnv and many other things. And then the most important function we provide to people is called execute with time limit. So Unsolved has this function called execute with time limit, where we set it to 2 seconds. We do not want a process to run for infinity, right? So we don't actually want this. And so we actually have a decorator to decorate any single function to execute a strategy in a specific time limit. And so this is actually very important because pretend some sort of strategy executes for 10 minutes or executes for infinity, right? We don't actually want this to happen. And so this essentially guards these functions.
What happens if they have to end fast?
Oh, sorry?
Like which action ends up getting picked, basically? Like if you have a very tight time limit.
Oh, yes. So if you have a time, so generally we found 2 seconds to be actually okay. You can increase it to like, for example, 10 seconds. Like if you want to have like a longer training run, maybe increase it to 10 seconds. But in general, because it's just generating a strategy, the strategy, you don't need to, so the execution of the strategy is separate from the actual generation of the strategy. So this execution of the strategy, we don't want it to last for too long because otherwise it would just be it would just take too long, right? So 2 seconds generally for execution is actually not that bad because, CPU execution of the environment isn't that long. But the generation is actually fine. We do not put a time limit for the generation of the strategy. Does that kind of make sense? Or
It does, yes.
Okay. We also, for example, convert the board to like a more nicer format for it to like, to process. And so there's lots of functions which we provide to like make the process easier for people. For example, let's try a strategy, a very dumb strategy. We just move left, right? Always move left. And we see it timed out, right? So we do not want this strategy. This strategy is not very good because the only thing it does is it just keeps moving left. So essentially this guard allows us to filter out, like repetitive actions, repetitive strategies, and also strategies that go in a loop. And so if strategies that go in a loop, this function can help like stop those types of functions. Yeah. Oh yeah. For example, here we, instead of doing 2 seconds, we actually set it to 5 seconds in the notebook. And so now I'll be talking about reward hacking, for example. So, previously reward hacking does cause problems for reinforcement learning. So now I'm going to tell you how to like guard these types of issues. For example, the first one is how do we stop, invalid code execution? And so, for example, this is fine, right? If you import generic Python functions like, the math library, types and stuff like this, this is fine. So we expose a function called check Python modules inside of Unsolved. And this essentially checks, is the function, calling some other function that is not a generic Python import. So this is good, right? So like, this is true. So this is very good. However, if we import NumPy, this is not good, right? So essentially, this function checks dynamically what packages are imported inside of these functions. And if this is not good, then you decide, okay, I can see this is a NumPy function. Do we penalize this? Do we continue on? And so this is one way you can stop reward hacking. For example, we just tell the model to generate fast matrix multiplication kernels, but then all it does is it uses NumPy or PyTorch, right? So we don't actually want that to happen. And so the goal of this function is to stop the strategy from, stop the model from generating strategies to use PyTorch or to use NumPy if you want to make faster matrix multiplication, for example. So definitely use this function.
In the context of 2048,
yes,
how could the model cheat if it had access to NumPy? What could it do?
That's a great question. I think in the context of 2048, that's probably unlikely, actually. I think these functions we just expose for generic notebooks. So for example, we have a matrix multiplication notebook as well. This function definitely will help for that. I think for the 2048 game, okay, I can give you an example. This is a very dumb example, but for example, let's say inside of the function, it actually calls another language model. For example, let's say it calls Gemini or GPT-5. Let's just say that happens. Or it calls some sort of server, which lets someone play the game. It generates a strategy by itself, something like that, right? So essentially we disallow any single function which does something like this. For example, importing OpenAI's library, for example, that's not allowed. Importing Gemini's library, that's not allowed. So I guess it's probably not a good example, but something like that. I
was kind of curious, how do you think about the prevention of reward hacking a priori, right? Because I guess we have intuitions of things we don't want the model to be able to do, like the examples you gave. But what kind of signs do you look for in training that give you some hint that the model's been hacked? Because you could say, oh, the reward is going up, everything is great, but the reward is going up because of the hacks. And I'm curious, what do you guys do at Unslot to sort of understand, okay, I've been hacked, basically?
Yeah, that is actually that is a question also for large labs. I think everyone's asking this question. It's actually it's one of the most important questions. The main issue is we don't actually know if a model is reward hacked or not. Even if you use LLM as a judge, for example, if you ask a language model to verify if the RL output is reward hacked or not, it's still very hard, right? How does a language model even know it got reward hacked? And so generally what we tell people to do is every single 10 steps or 100 steps, you would sample, you would stop the training run or just look at the output and manually inspect, does it actually look correct? So I would say it's more like a vibe check. The other approach we had is you should, for example, you ask another language model, during the LLM as a judge phase, and you don't actually touch it at all, right? You don't train it. You don't use, so there is another approach. You can use the same RL model to judge itself. That's what people like to do. But our view is you probably shouldn't do this. You shouldn't do this using the same model to judge itself approach. You would rather just use the previous SFT model, at the very, very, very beginning of training, and then use that to judge the model. So that kind of works. I think, in general, what we find, I think from experience, if the model is reward hacking, that is a good question.
I think one thing I've seen myself is if you look at the lengths of the rollout.
Yes, I was going to.
Yeah, exactly. There's often a hint when things are going off the rails. So even though your reward curve can look great, if your rollouts are going to infinity, it suggests that the model is exploiting some peculiar tokens which are getting high reward.
No, yes, I was actually going to mention something to do with length. Looking at the metrics, so looking at, for example, using Track.io to look at the metrics, definitely look at all of them. That is very important. I think, actually, there is one way. So actually, I did remember. So if you make more reward functions, generally, you won't see reward hacking. If you make independent reward functions, and not just one. So generally, what happens for reward hacking is people just make one reward function. For example, is the maths, is the code output good or bad? Is the maths formula at the very end correct or wrong? And if you have one reward function, you don't actually know if the model's reward hacking or not. So what normally people should do is you should make multiple reward functions that are independent from each other. And if you can do that, generally you can like reduce the probability of reward hacking. So for example, for maths, do LLM as a judge, but don't just do one model, like, call the model 10 times for LLM as a judge, and check, or maybe, something like that. But like essentially make more reward functions, and you can reduce the probability of reward hacking.
Cool, awesome, thanks.
So like, that's a NumPy example. The other very important one is you want to create a locked down function, which disallows global variables. So one of the things in reward hacking is the language model can actually write to the global space of your programming language. So that is not good, especially if you're doing like some sort of benchmarking or kernel creation. It can actually do caching. So if it does caching of the results, you will actually get incorrect results, but your reward is still going to go up. And so this, locked down function approach essentially locks down the, function to only call, non-global variables. And so, this is definitely very helpful as well. For example, we did not, so this is just a NumPy example. We didn't actually import NumPy over here, right? So it's supposed to actually do import NumPy. But we didn't actually do this because essentially NP was a global import. And if you look at this, create lockdown function, this is disallowed. And it will tell you why this is disallowed because NumPy is imported. So definitely also use this. For example, this is the one that succeeds. You can nested functions are fine. So this should succeed. And yes, it definitely succeeds. So create lockdown function supports nested functions and recursive functions. And so this is the most important part for reinforcement learning. If you want to create a 2048 strategy, the trick of reinforcement learning is you only need one prompt. And so the difference, so I always get the question, what is the difference between supervised fine-tuning and reinforcement learning? If you have lots and lots and lots of data, you should do supervised fine-tuning. If you do not have data, you should do reinforcement learning. For example, for the 2048 game, there is no data, right? I'm telling the model to create a short 2048 strategy using only Python code. And this executes the strategy, right? This is the only prompt I give the language model. It's just one prompt. Imagine you can customize this, create a trading strategy to do blah, 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 or, do some weather simulation, predict some new chemical or something. I don't know. But essentially this prompt, you only need to engineer this one prompt. And you replicate this many, many, many times for reinforcement learning.
Daniel, I had a quick question from the section we just passed, which was really about the reward functions. And it was basically, in short, have you ever explored like pure rubric functions, so rewards that we don't necessarily use to update the model? I know when we were doing Wordle, we used that a lot, mainly for the smallest models, like under 1 billion parameters, where they would, for example, just repeat themselves 5 times. So we wanted to just understand like what they were doing and kind of track that over time, but not necessarily reward that. Like we had better signals for reward.
So do you mean like, for example, if the model kept repeating like a strategy, or like, for example, as you said, repeating, would you how would you use the rubric? Would it be like just discard the output, or would you like reward it somehow?
So basically, it might just be a specific artifact, but in this example, the models, these small Quen models, consistently created the same guess.
Yes,
and we
correct.
found that we had a richer reward function that was for yellows and greens in that game.
Yes.
And it started off quite low and it would build up, and it was just very rich reward function. And penalizing repetition just didn't have as much information. So in TRL, what I could do is just like say the weight of that reward function is 0. So ignore this reward function. But then when I'm watching and monitoring my training process, like I've got quite a good view of like what's going on. Okay, this is another kind of repetition run. Let's try something out and go back.
Yeah, so generally what we see and we tell people is like you can also do something called dynamic weighting. For example, if you find your rubric function or like some sort of style check at the very beginning, is somewhat helpful. Like, it's somewhat helpful, but then over time, it's not that useful. You can essentially decrease the weight over time to make it go to 0. So you don't actually have to set the weights to go to 0, like weight as 0 at the very beginning. Maybe you should set the weight to be like 10 or something, like some sort of number. Okay, so obviously it has to be normalized. But essentially you can decrease the weight over time. I'm not sure if does that kind of answer your question? I'm not sure. Maybe
that is a really cool idea. Yeah, I definitely think that would help in that situation, because that was the problem. After a certain number of steps, that function became like regressive, basically.
Yes.
And
yeah, exactly.
So it probably would have learned from it in the first kind of 100 steps. So cool. I'll take that away and try that out. Thanks.
Like another good example is like length. For example, if you want the model to do okay, you should not, at the very beginning of RL, the responses shouldn't be that long. So I would, like, for example, penalize length. But then over time, the model gets, the model has to understand more complicated questions. Then you would like not penalize length, right? You would decrease the weight of the penalization of length over time, something like that. And so like these dynamic weightings of the, reward functions, I guess that's another hyperparameter, another turning knob. But I guess like, yeah, but definitely like, dynamic weighting is like an active area of research for people. Yeah.
Cool. Okay. Thanks for that.
But yeah, like for example, we create this one prompt for 2048. And then if we call GPT, GPT-OSS, it does okay, right? It generates some sort of strategy, right? This is no RL, right? No RL at all. And so it does generate a strategy. And then, during the RL process, we want to improve the accuracy of GPT-OSS. And so we actually kind of created some reward functions as well for 2048. For example, the function works, no cheating, and strategy succeeds functions. But firstly, we actually need to extract the function. So previously I said, like, for example, you need to generate it between 3 backticks. And so we need to somehow extract this from the generation. And so this function kind of like extracts the strategy. And then for example, we use the check Python modules function to check, does actually the function, the strategy, only use Python functions and not like NumPy or PyTorch or something like this. And so this, we utilize this function inside of this function works reward function. And if we find an error, then we penalize by -2. If we try a lockdown function, so because of Python's very good because we can do like try and excepts. And if we create a lockdown function and it succeeded, we score a 1. And if it failed, then we score -0.5. Another question I always have is, how do we actually allocate these numbers? Like what can they be? And so for reinforcement learning, they can be anything you like, right? It can be -20, -10, minus whatever you like. And so these numbers are up to you to decide. But in general, I see like normally people do 0, 1, binary, or just -1 and 1. But it's up to the practitioner to decide.
If either of you could interview for, I don't know, could intern at Anthropic for a day, like what would you do to solve coding models using excessive try except blocks?
Is that a question?
Yes.
Or can you repeat the question? So Anthropic what? Sorry.
Yeah. So like a lot, like one of the sort of the most annoying code smells in AI models is their excessive use of try except blocks.
Yes.
How would you go about fixing this problem so they're not as defensive?
That is actually a very good point. For example, I was like, when you do, actually, I just experienced this a few days ago when I was trying to use like AI models to like, generate code for like, training. It keeps doing try and excepts for like, especially torch functions, try to import this torch, like for example, torch _dynamo reset to like reset the compiler cache. It tries to like always do this, try except, try except, try except. You could, I guess, force the system prompt to say, not to do try except. It doesn't really work.
Still does it. Yeah, that still does it.
Yeah, it doesn't really work. I would say that is actually a very hard problem. I'm actually not sure why it does lots of try excepts. My view is because the language models are very pedantic because it needs to consider all versions of packages. For example, PyTorch, for example, some functions are not existent when it's PyTorch 2.000, right? So like it doesn't actually have a specific function. Or, PyTorch 2.10, right? So it has a specific function. And so that's that's what I see when language models generate this. It's because it considers too many factors, right? It understands, okay, what happens if PyTorch the version was 2.8? That's why I have to do a try and accept. Or I guess you could specify, all the dependencies, like, you are using PyTorch version 2.8. That could help. To be honest, I don't think so. I think I tried it before. It doesn't really help. But I think that's a great question. To be honest, I'm actually not sure. That's a very good question. Yeah.
Yeah, I don't know the answer for the specific case, but I think in the RL context, one of the things that might work would be using like rubrics as rewards. So the idea here, I mean, there are many papers doing this in various contexts, but the idea is instead of having a single outcome, like, correct, incorrect for my reward, I have a way of assigning like partial credit, and the partial credit is based on like a series of like heuristics. So like in the context of say math, you would say, okay, I grade my proof with like a bunch of things, and if the model, for example, makes like a dumb mistake, like an arithmetic error, it gets like a clear deduction from the rubric. And so you could imagine a rubric for a certain set of tasks. You'd say, okay, like even if you get the answer right, you get some partial reward, but you get deductions because you used, unnecessary try accept. And the way you would have to then do that is get an LLM doing the grading. So as long as the LLM is good at identifying, whether this is like a good or a bad example of try accept, depend on it. But I suspect that probably helps.
Yeah, I was gonna say that's actually a good idea. Like, for the reinforcement learning side, like, if you keep seeing try and accepts, maybe like add some sort of counter. If you see a try and accept too many times, divided by, how many other things you see, then penalize that. I guess that could be, but is Mark's question like about reinforcement learning, or is it like a generic, like a language model type thing, or is it like for reinforcement learning?
I mean, I think this seems to be like a unique property of like it's more egregious for reinforcement learning for RL models. My suspicion is this is like a hypothesis. It's just that like if they're using a rubric, then correct code is really important, and that like trumps a lot of stuff. And then if you try accept everything, your code's almost always going to be correct or have some sort of reasonable behavior, like just reasonable exit codes. Anyways, yeah, maybe I'll just try to ask friends at Anthropic if they're actually working on this.
I was gonna say that sounds more like an actual case of reward hacking, I guess. Like, essentially you just add tries accepts everywhere to solve that one correctness. It has to be correct, or okay, maybe that's interesting. But you're right. Like, I do always see generated code with try accept, try accept, try accept. But to be honest, I think like Python's pretty cool. Like, I think Python 2.10 or I think it's 2.10 or 2.11. Try accept anyways doesn't take any time. There is no overhead with try accept, unless if you enter the accept region, then it's actually slower. So that's the only problem. Yeah, but I think like what's wrong with try accepts? It's pretty cool.
All right. Well, okay. I'll let you guys keep going.
But yeah, like, so the last, I think there's two more, but no cheating. Essentially, if we, if the model cheats, if it uses NumPy or PyTorch and stuff like this, then, again, we will like penalize this. And another one is if we find that the model doesn't actually follow the format, we will actually we will penalize this quite heavily. And this -1. And if it uses Python functions, we will do -20. This is not allowed, right? So we will never allow this to happen. And so we give like, you can also do -200, but try not to make too large numbers because, this will skew the training process too much. Yeah. And, we just we place everything into like one large function to like check if the strategy has succeeded. So this actually executes the strategy on OpenEnv. And, this also has a timeout. Like, for example, we used execute with time limit. So we don't actually want the model to like, execute the strategy forever. And if it does succeed, we massively reward the model. And if it failed, we still rewarded a little bit because it kind of worked. And for timeouts, we will, reduce the reward for these timeouts. And yeah, so like we essentially take the one prompt that we had and just multiply by 1,000. So it's the same prompt over and over again. You can so if you're a large lab or like, you don't just want to do one example, then all of these, it won't be the same example, right? It will be like each of them will be different. But in this small example, we can just use 1,000 of the same prompt. And then we'll be using TRL. So like essentially Unsoft, works on top of TRL to make it much more efficient and use less memory. We also use Track.io to like track inside of the Colab notebook, the logging. And so once you actually get to the training stats, you will actually see the strategy that is generated. And, for example, this is at the beginning, and over time, you will see, lots of strategies generated. And the goal is you have this large table of numbers, and the goal is you want the reward to continuously going up. And so the goal is you want to just look at this column and see if the reward is going up or not. And you can look at the other columns, like for example, different reward functions have different, rewards. Definitely look at that. For example, function works is very important. So like, definitely check if this column is going up. And, this table is very important. So definitely keep a track of this. Yeah. And yeah, like I think and then you can save. So for example, at the very beginning, once you actually finish fine tuning, you will get lots of strategies generated. You can like, do inference. For example, after the reinforcement learning run, what does it generate? And then it kind of like generates a better strategy now. And then finally, because this is QLoRa, you need to use save pre-trained merged or use the LoRa adapters directly, right? You should not upcast the 4-bit model to 16-bit and then merge the LoRa weights. This will actually damage the model entirely. We actually did many experiments, and I think this reduces accuracy by like 30% or something. And so definitely don't do this. Instead, this function takes the 16-bit weight and merges it directly inside. And so, yeah, you can upload to Hugging Face and stuff like this. Yeah. And also, like, as a final note, we also have a guide which you can go to. If you want to read more about Jupyter reinforcement learning, we have more examples. And there's also a reinforcement learning guide for people who like want to learn more about reinforcement learning. For example, Pac-Man example and stuff like this. Yeah, but that's about it from my side again. Yeah, thanks.
Awesome. If I may ask one final question. So about this time last year, DeepSeek R1 came out and broke the internet. And kind of, I think, made RL go mainstream. So, we've now had a lot of practice doing RLVR. I'm curious where you think this year will go. So where do you think, what role does RL play in the field? And are you expecting any other, bombshells?
That is a very good question. I'm assuming lots of labs are going to be releasing lots of cool models this year. Obviously, DeepSeek's new model is very interesting. So I think it's like next month or something, according to rumors, during Lunar New Year. So I'm waiting for that. Supposedly, so the view is So the main view of large labs is reinforcement learning should continue to scale. I'll be interested to know, will reward hacking cause a bigger headache than actually if you scale reinforcement learning? So actually, my take is reward hacking will actually take over. And because you could hire data labelers, for example, you could go to Mercor, you could go to Scale to data labeling. But the view of large labs is you want to automate this away. So my take is you don't actually want data labeling. RL essentially can automate reinforcement learning, right? So RL can automate RL. And so I think maybe this year we will see less usage of data labelers. My view is we should have models create environments as well, and let humans also test, does the environment is the created environments actually good or bad? And these automatically generated environments can probably be used for RL as well. And so that's kind of my view. As we're going to be, maybe this year we're going to be seeing automated RL environment generation. And my assumption is OpenEnv will also have something like this inside. And so that's my kind of view. Yeah.
Cool. Thanks.
All right. Okay. So we have our last speaker of the day, which is Zach Wentz. Zach, please take it from here. Let me share your screen. Zach, do you want anyone else on the stage with you? Yeah, Davide. And then I will go away.
Zach,
you're both muted. Yeah.
Can you hear me now?
Yes.
Okay, perfect. Well, we're running a little bit behind, so we'll jump right into it. But Davide and I work closely here at Meta on the PyTorch team on OpenEnv and other things. So this talk is entitled CPU Mode. We've got Slow Goku there representing the CPU. And we're going to talk about, in this talk, a little bit about where we think things are going, as well as the side of the fleet that when we're talking about reinforcement learning on an environment that you're not considering. So the GPU fleet gets all the attention, but we have to scale up our sandboxes alongside it. And our sandboxes are lower than our GPUs. And so we've got to scale it up quite a bit. Yes, it's cheaper, but it is compute you have to think about. And you'd be surprised how frequently people do forget about it and how surprised they are at the size of compute we need. We're going to talk through some of the scaling problems in this session. So throughout this whole thing, we're trying to maximize throughput. This sandbox demand formula here that we have, I think is a bit outdated when you move into the world that we're moving into with really long trajectories that you're trying to train on. As this increases and as they continue to be stateful, we start to lose the tricks that we had before. And we'll talk about some of those. So just to give you a background, like what do we do? Been doing this for about a year and a half now. Started out as like code interpretation, simple tool for Meta AI. And it's grown increasingly since then to where today, we are supporting at any given moment, the platform is supporting 10 million or more concurrent sandboxes at a steady state. And we have an order of magnitude bigger spikes. Our pre-warms, 150 milliseconds, pretty much standard. There's folks like Daytona, for example, that are doing better than this. But at a certain point, you're running into the laws of physics with network requests anyway. So it doesn't matter much at a certain point, especially on a long trajectory where you amortize that cost over a long time. For cold starts, we'll talk about different regimes, but for cold starts, we got those down as well. We're using Docker layer caching, and we're using registry peering as well. So I say registry peering. We're peering from the hosts that are executing these sandboxes, the different layers, rather than going back to the registry. That's the better way to think about this. We started with batch snippet execution, and we've now moved throughout the entirety of the pipeline, pre-training, post-training evals, really long trajectories. We're moving into inference. We'll talk a little bit later about the year of the sandbox. Scaling regimes. So there's two main scaling regimes to think about that you need to scale differently. So there's the hot path, which is, these are our battle-tested environments. You can think of image and environment as sort of interchangeable here, but these are our battle-tested environments. These are ones that we're using for a well-honed use case. We've gone through all the stability and reliability issues that we've had before. We're going to pre-warm a pool with these. We know generally how much we're going to be scheduling for at any given moment, and we're going to cache a lot of those image layers just directly on the host itself. And we're shooting for 200 milliseconds or less to get started. This is typically what you're going to see in like when you finally got your model trained on some agentic workflow, and now you want to deploy this agent with an environment. You're going to be looking at the hot path. The long tail is where we talk about like getting a generalizable model. So you've got a bunch of different unique environments. You have a very different scaling form here. So you can't pre-warm all these. It's just not possible. 500,000 environments, that's not going to work. So you need some other mechanism. This is actually where like OpenEnv starts back in the day, which is we need some base image with a lot of common dependencies. Everyone is authoring these environments in different ways. They're, you can even have the same dependency, but if you have like one version number off or something like that, it's going to have a different checksum, and now your cache is less effective. So getting as many common base layers as we can get in some so our content addressable layer caching works, is something that OpenEnv can start to help you benefit from when you're running Docker environments. There's also microVM environments, but those are a little bit different. We'll talk about that. But here, you're generally shooting for less than 10 seconds of startup time. The lower you get, the better, but again, long trajectories. The other thing to talk about in terms of regime, where you can get some performance improvements, is how much do you trust the workload in this environment? So like we started all this in the sandbox from, I want to lock down generated code that I don't trust. But we are starting to see companies training on, we're training on it too, internal services, right? We trust those services. We wrote those services. And so there's some like semi-trusted place here where we trust the services code. You can't do too much as an agent in this environment. And so we will relax some of the protections we have here, and therefore will be faster to execute and run. And then there's this trusted territory that, starting to see pop up. We don't necessarily have this use case yet, but it's something to start poking on. This is where you could just run a container as is without like a VM sandbox around it. And Davide, please feel free to chime in at any point to add color, but I think your slides are coming up. This one was kind of a big one for us, middle of the year. I alluded to it in chat. The registry bottleneck. So once you get to where like the infrastructure will scale, it starts to become just a problem of moving bits around. And that's where you get into the work we've done on like the high cardinality side. If I go back to this, to the long tail, just getting these bits onto a host starts to become a real problem. And so you may have like Docker aware caching, where you're caching the layers. But if you're not peering those, you're just going to be slamming your registry with a ton of requests anyway. Even though it's a small, just what we need that isn't cached locally, it's still going to overload your registry after a certain scale. At one point, I believe, just as like a fun fact, at one point, without the benefit of peering, our cache was like a fourth of Facebook's entire cache just for sandboxes. We quickly had to get out of that, but for a brief period, that's how big it was. VM snapshots. So this is something else. One of the things that we're not doing, but that you can do, and a lot of sandbox platforms do, is to make your cold start even faster, right? You don't have to boot the Docker image itself. You can, upon ingest of a new environment into your registry, go ahead and spin it up, and then right at the point of being ready to execute in, take a snapshot of your microVM and store that. And actually the layers of that are easier to cache than say Docker layers. You don't have to do all the work to make them common necessarily. But then when you spin it back up, it's like 4 to 10 milliseconds to be ready to execute. And so then network becomes your bottleneck. Lots of folks do this. Lambda snap start is a great example of that, where your Lambdas run fast. But again, it stops helping, and that's the direction we're going generally, is long trajectories, network bound. So this is like the two ways to reason about it. It goes back to those trusted regimes or not. This starts to lead into something that I want to talk about today, that I'm like most excited about this talk to talk with you all about, which is where we see this going, which is a combination of these two things. So why do we see it going in this direction? I think everyone is doing Claude code, dangerously skip permissions. You get tired of accepting permissions. It was trending on Twitter just this morning, people complaining about the frequent permission prompts, even when they say, they didn't YOLO it, but they said bypass requests. They're still approving a lot of stuff. Where we're going to see this happen more often, though, is not from like user fatigue, but from sub-agents starting to take over. When you Ralph Wiggum your Claude code, you're not going to want to inject the human back into the loop to go start approving permissions. You're just going to say dangerously skip the whole way. And so you're going to need a safe by default sandbox to operate in. as opposed to flagging it to say that you can be dangerous. That's where we're going. And the reasons why Davide can speak to more so, but how we see this starting to combine, and this is where I want Davide to jump in as well, is I've been calling it an agentic kernel. I think probably from this talk, the better way to look at it is an agentic microVM. But like, imagine a world where, you know, you have your Docker image, you have your microVM that starts fast, it's safe. Your Docker image, though, is easy to author. It's quite observable. And you can put the dependencies you want in it with ease. Imagine a world where these two combine. I think we're quickly headed in this direction. I think we'll see multiple projects like this ship in 2026. I think you might see me and Davide's face again talking about this in 2026. I think it's quite exciting. I especially think the architecture bit of this is very exciting, which is thinking about an execution environment and an agentic environment as one and the same, but with separations, much like we have the Linux kernel today, where you have kernel space and user space. Using that same metaphor, but applied to this problem, I think brings some very interesting things that we can start to do and that we need to do in order to keep going in the direction we're going with all these agents supporting us.
Yeah, and to add color here, I think that what we're seeing is, as things become more clear, this is an entirely new world, right? And so as things become more clear, I think it becomes obvious that some of the infrastructure that we had was built for similar but fundamentally different use cases and different requirements. And so this is what we're going towards. And I think that this intersection of like low trust but high performance is something that was not exactly quite touched upon by the existing systems. And so you're going to see a lot of activity here and from us as well.
This is pretty cool. Like, I guess I had two unrelated questions. Zach, you mentioned something around like private Docker registries being rate limited. Is this like a fundamental technological constraint, or is just like a policy choice on their end? Like, because that just feels like, why have it at all for private? Doesn't feel like it matters.
Sorry, I didn't mean to say necessarily rate limited so much as like it's limited by the pipe that you have. So like even internally, we had this conversation about the number of images in our registry. And at a certain point, we realized we had more images in our registry than Docker Hub has accrued over 14 years. And we're pulling them at a pretty active clip and concurrently. And so we were just bottlenecking. Like we could not, no matter how much bandwidth we threw at it, how many hosts, get enough through the pipe to make this work at the scale we wanted to. We had to move to something like peering.
I see. Interesting. Okay. Or I guess like the simpler solution would be like just have a lot less images internally too, right? But that's probably it's much more politically difficult. And so then the peering ends up, okay.
Yeah. Well, and that is where a long trajectory, for example, might help, right? Because we can keep the image more common and we can accept some build step configuration that an environment author might do, to where they say, once we've got this image up and running, you need to perform these few commands. Yes, it's going to take a bit of time, but amortized over the time that we're going to be interacting with this environment, that's fine. And then your images become much more common, but your configuration starts to change a little bit, and that's nothing.
And sort of the second question is like, I think because this is very timely. I think like yesterday, like Anthropic released like their coworker product, and I think people sort of reverse engineer it and figured out that it's like some using some container service on Mac. As you look at it, do you go like, oh yeah, like makes sense, or do you just feel like containers are fundamentally the wrong level of abstraction here, or is it like just good enough? And then there's like a few patches we need to do here and there.
Yeah, I think, I mean, I'd be curious to hear what Davide says, but I'll just jump in with my own answer to start. I think that containers are the choice right now because they're easy to author and easy to set up. And researchers are driving a lot of this, and that makes its way into a product. And if we can make it such that something like a microVM is as in distribution, such that you can vibe code it, right? As Docker is today, to where a researcher can start from that point and where safety, you start from safety, and in fact has some agentic primitives to where they would want to do that in the first place to help sweeten the deal. I think that tips things in the favor of microVMs, which are going to be much faster and safer.
And specifically, if people are interested in the space, like which projects would you recommend they follow? Like, is like Firecracker, like for example, like one good one, or are there others that you're interested in?
I would look more at the Sandbox providers, especially the cutting edge ones. So I would look at Daytona. They have got their thumb, like I don't want to say thumb on the scale. That's the wrong way to think of it, but they know where this space is going. And they've got a good sense. The other one is Sprites.dev. They rock. They've built like, currently I would say that is like state of the art that you can buy and at least that you should follow for a sandboxing platform. Like it's awesome. I think it nails it.
I think I'll invite them for a talk then. I really don't
Yeah.
want to rush you guys, by the way. I just looked at time. I have a hard stop, so I think we have about maybe 7 minutes for y'all to finish up, if that's okay. And then I just want to give everyone the chance to do some closing thoughts as well in the end.
Davide, did you want to answer that question as well? Like provide or did you?
I think you are the better person here in a way. So like I think for everybody else, I think our relationship is more on the kind of machine learning side or else side, and so I kind of pester Zach with requirements, and then Zach figures out how to get it done. But I think that this actually works because I think that ML researchers tend to kind of do whatever to get unblocked, and so we get to like these big repositories where like 90% of the code is not necessary. It's just there because we didn't have proper abstractions, the proper infrastructure. And so I think the one way of measuring, whether we're going to be successful here is really to see this, like the size of ML projects code kind of go down and become like a one-liner where like, okay, obviously the sandbox is doing what it's supposed to be doing, and therefore I can just trust it. That's kind of where we want to be.
Yeah. We honestly, I think to TLDR that, like we're talking a lot about sandboxes right now. We probably shouldn't be talking this much about sandboxes in the right future. It just is a solved problem. Just like we don't talk a lot about Linux unless you're on my former team working.
Yeah, exactly right. Think about going to like reading a file on disk, right? We just read the fucking file.
I'm sure there's a way. It's there.
All right, I'll let you guys then finish things up. I'll go away.
This is the last slide. We end with questions. So, like I said, I think we could do your timing, Mark.
I think I want to talk more about sandboxing then, if that's okay. Let me also bring everyone on stage. I think in case people want to also jump in with other thoughts. Here, I'll remove this.
Should I kill screen share and we just vibe it out?
So for example, one product that's been a favorite of people in GPU mode has been Modal. It's also sort of sandbox execution of simple code. And I think we've really liked it because you can do these kernel micro benchmarks very easily. It's quite cheap because it's queue-based. It has just been overall a wonderful experience. I'm not sure what their secret sauce actually is to make sure things run really fast. But I'm sort of curious. I guess Zach, you surprised me to say it seems like there's actually a vibrant space and many people have products and opinions, and I'm sure cold starts are important for them. And so I'm wondering if you could just maybe elaborate a bit more on projects you'd like to see here.
Yeah. I mean, so we've even used Modal. We talked a little bit about that Code World model paper earlier. Lewis did. A lot of that was trained in Modal. A lot of it was trained in the platform that I support at Meta. I think Modal does some really good stuff as it relates to developer experience and working around some compute constraints that we haven't had to do. And in fact, we need to do now. We probably need to catch up on DevX internally. I think Modal, they don't have secret sauce. I don't think they're all that fast, if I'm honest. And I think they've got they found their niche. I think there's faster ones that are more on where we need to be. Sprites being the top one in my list. But yeah.
Sprites. Okay, let me take a look. I see, and I guess eventually your hope is that this is maybe a question relates to Ben, which is that there would be all these sort of, I forget what was the terminology you used. It wasn't backend, it was something basically you had the UV thing, the Docker thing. I think you had terminology
The providers.
the provider, yeah. So you would imagine that eventually these like sandbox environments would be like providers, and they'd be sort of like very additive to the work you're doing.
Yeah, I mean, so the interactions that we're having with researchers are, as I said before, at the opposite end of the scale to Zach, and they're like often like researchers in university labs. They've got a series of very interesting environments that have come out of a paper, and they're probably quite hacky, and they're not necessarily something you can combine. And so kind of OpenEnv brings that layer to that environment that you can then make it interoperable. And you can take something like a provider, and it could start off as like a just local Docker provider. I want to evaluate this environment. And then you can plug in like Slurm and Kubernetes provider with the same abstraction and just kind of deal with that.
And I guess like then question maybe more to Louis, Daniel, and Davide, like, which is like it seems like, I mean, y'all are a bit like from different, like slightly different worlds, like, which is like there's sort of the like what I would call infra, and then there's like the MLSys infra with kernels, and then there's the science. Like what kinds of tools like do you think would make your life easier? Like where do you think like this whole ecosystem of RL is really underserved? Do you think like fundamentally these are like the important pieces and people should keep going? Yeah, any sort of open challenges you have to people in the GPU mode server?
I think the biggest pain point I've experienced is that the field of like say RL algorithms moves relatively fast. So there's like a lot of like, I mean, there's all the permutations of GRPO now that you can imagine, and it's never entirely clear like if they are meaningful improvements or if it's just, you know, like noise in the eval or something. Like these things are like quite hard to validate and test. And part of the reason why it's tricky is that some of these things work at one scale but don't work at another. And my experience so far with like the open source ecosystem is like with the RL tooling, we don't really have anything, I think, that is like probably what like is internal at like OpenAI and other labs, which like lets people do this like fast experimentation at different scales without having to think about, okay, what do I trade off if I want to go to like 100B versus 1B? Most of the open source ecosystem is like fragmented in this thing, is like they target one of those axes of scale and then they make that work, but then you make trade-offs. So I think a bit of an open problem is like better kind of tooling overall to make that thing easier. And the other thing that's still a bit missing is like the observability of like RL runs. Like we have metrics like reward and stuff, but like, you know, having ways to kind of easily collect all the rollouts and like inspect them and do that kind of stuff. Like this is still a bit early. So that's my 2 cents.
I think in my case, the feature that also will intersect the most here with this audience is also parallelisms. That has been, I think it's just, they're not into, at least I've never found them intuitive. And especially like once you start adding 4 or 5 dimensions of parallelisms, it's very hard for me to keep track of what's even happening. Like what work is being done by any GPU at any given point in time. And certainly you can treat these as hyperparameters, you know, sweep them, figure out where you have the most throughput and whatnot. But at the same time, you know, onboarding new models is difficult, and starting to do a bunch of these wizardries with interleaving forwards, backwards, and all the stuff that DeepSeek has been doing is just a major kind of slog on kind of my understanding of the flow and my productivity in general in onboarding new models.
That's a really good point I just want to iterate a bit on, is like the ecosystem has migrated to a mixture of expert models, like pretty uniformly. But most of the tooling for training is not really well suited for mixture of experts. So you kind of have like this hard choice. It's like I use Megatron from NVIDIA, which, you know, is very powerful, efficient, but has its trade-off that it's like not perhaps the most user-friendly. And then you want to say go to Torch Titan or Torch Forge, but then you sacrifice like genuine performance. And this is like a bottleneck. And I think we don't yet have in the open source ecosystem something that is like flexible, but really highly performant for mixture of expert models. And maybe that will come this year, I guess.
All right, then I'll close things maybe with one last question. I think this is directed to Daniel, but if anyone else has a hot take, I'd love to hear it. So Dan, I think when you first started Onslaught, like it was kind of quite clear, like basically there are important LLM kernels, and you had like written them all out like in Triton. These days, it seems like you're reliant a lot more on other libraries, right? Like you're relying on VLM and like these like training libraries. Do you worry then about numerics? Do you feel like the sort of concerns around this are a bit exaggerated? Are you planning on just rewriting everything with your own kernels? How do you sort of think through this, like a bit of a longer time frame?
Yeah, that's a great question. Yes, we did start off with Triton kernels, and like it's great. But I think, to be honest, I think I would divert the workload to the PyTorch smart engineers, right? So like my view is Torch compile will take over. And so like I think, so there are two types of algorithms which still cannot be like, so there are two types of algorithms. There's like kernel fusion type algorithms, and then there's actually mathematical type algorithms. So Torch compile still does not do very well with mathematical type algorithms, right? So like data movement, essentially for data movement changing. So changing data movement patterns. For example, like flash detention 3 or flash detention, it's more like data movement. And it's probably hard for Torch compile to like do something like that. For example, like async grading checkpointing, or like, chunked losses and stuff like that. However, my view is like, maybe over time, there are like specific methodologies which are like repeatable. For example, like chunked losses, it might actually be, inside of Torch compile. It might be like some sort of setting, right? Everything can be chunked. Everything can be like async to like RAM and GPU memory and stuff, like something like that. So I think like my take, I'm not sure if that's probably correct, but like my view is like Torch compile. Everyone would just use Torch compile and just enable it by default. That's kind of my view. But I think the only problem is like Torch compile does have a warm-up problem. It is very slow at the very beginning. But once you like, bypass the warm-up problem, I think like, Torch compile has like cache. So like you can use the inductor cache and stuff like that. So it does help. Yeah, but I'm not sure if that kind of answers your question.
It does, and I think we unfortunately need to end things here. But I think what I liked about your point is you're sort of suggesting that like maybe the kernels isn't really the most productive thing. Like for instance, I don't know if there's like tens of thousands of developers working on efficient sandboxes, but maybe there should be like a bit more than what we have today. So I think I will certainly be reaching out more with you guys like privately to figure out if we can do some more interesting working groups on the server, and if there's more open source projects that would help researchers such as yourself. But honestly, guys, like thank you so much. I'm very honored you made the time for this. It was 3.5 hours long. I think I was expecting only 2 hours, but yeah, this was very nice. So thank you, and I appreciate it, guys, and I'll see you soon.
Thank you, Mike.
Thanks for having us.
Bye, everyone.
Thanks, everyone.